Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're going to wander toward one of the strangest ideas in all of physics, not because it is loud or dramatic, but because it is so small, so fast, and so far beyond ordinary experience that the mind almost has to tiptoe near it. Our subject is the Planck frequency, sometimes described as the highest frequency that could make physical sense. That sounds simple at first, like we're merely asking how fast something can vibrate, how quickly a wave can rise and fall, how many ticks a clock could possibly squeeze into a single second. But as often happens in physics, the simple question opens a very deep door. Behind it are black holes, quantum mechanics, gravity, the limits of measurement, and the possibility that nature itself may not allow us to slice time forever into smaller and smaller pieces. Before we begin, I wonder where you are listening from tonight, and what the world around you sounds like right now. Is it late evening where you are, with the room quiet and the day finally loosening its grip? Is it early morning, with light beginning to press softly against the windows? Or are you somewhere in between, sitting in that curious little pocket of time where the clock says one thing, but your body says something else entirely? A topic about the fastest possible rhythm in nature feels oddly suited to a slow night, because the more physics asks how fast reality can tick, the more we are reminded to slow down and notice the quiet intervals between our own thoughts. If you find this kind of journey calming, or if it helps your mind settle while still giving it something interesting to hold, I would be grateful if you liked the video and subscribed. It helps this quiet corner of science reach more people who may also enjoy drifting through the universe without needing it to shout. And as always, I hope tonight is interesting enough to keep you gently curious, but not so exciting that it keeps you from sleep. Physics has a way of pulling on the sleeve of the imagination, but we will let it speak softly. So settle in. Let your shoulders fall a little. Let the day step back. Tonight we are not rushing toward the edge of the universe. We are moving slowly toward the edge of time. Frequency is one of those ideas that feels familiar long before it becomes scientific. You know frequency when you hear a low drum beat, slow and heavy, or a high violin note, quick and sharp. You know it when a phone buzzes against a table, when a washing machine hums through a wall, when a mosquito announces itself with that tiny irritating whine that seems designed by nature specifically to test human patience. Frequency is simply how often something repeats. A swing moving back and forth has a rhythm, a heart has a rhythm, light has a rhythm, though it moves far too quickly for our senses to follow directly. Even atoms hidden deep in ordinary matter have rhythms of their own. A slow rhythm gives us one kind of world. A fast rhythm gives us another. The slow turn of Earth gives us day and night. The monthly motion of the moon gives us tides and calendars. The very fast vibrations of molecules give us heat. The even faster behavior of electrons gives us chemistry, light, and the machinery of modern technology. The universe is not silent underneath its surface. It is busy with repetition, pulsing, cycling, changing, and returning. If we could somehow listen to everything at once, from the beating of wings to the trembling of fields, reality might seem less like a collection of objects and more like an orchestra tuning itself at every possible scale. But there is a question waiting quietly inside that thought. Can a rhythm be infinitely fast? Can something vibrate faster and faster without limit? Could there be a clock so quick that every other clock in the universe seems frozen beside it? At first, it is tempting to say yes. After all, mathematics can imagine any number it likes. If one rhythm is fast, we can imagine another twice as fast, and another beyond that, and another beyond that again. The human mind is very good at extending a staircase upward even after the building has ended. But physics is not only imagination. Physics has to ask what nature permits, not merely what arithmetic can write down. That is where the Planck scale enters the story. The name comes from Max Planck, the German physicist whose work helped open the door to quantum theory. He did not set out to invent a mysterious boundary at the bottom of reality. Like many great shifts in science, it began with a practical problem with heat and light and the behaviour of glowing objects. Planck found that energy, at the smallest levels, seemed not to flow in a perfectly smooth stream, but to come in tiny portions. This was the beginning of a revolution. It suggested that nature, under certain conditions, is not infinitely smooth. It has a kind of grain to it, a smallest meaningful packet in some situations, a way of behaving that refuses to match our older expectations. From Planck's work came a set of natural units. These are not units invented because a king's foot happened to be a certain length, or because a culture divided the day in a convenient way, or because a committee agreed on a standard. They are built from constants that appear to belong to the structure of nature itself, the speed of light, the constant that measures the scale of quantum effects, the constant that describes gravity. When these are combined in the right way, they produce quantities that seem to point toward the deepest borderlands of physics. There is a Planck length, a Planck time, a Planck mass, and from Planck time we can speak of Planck frequency, the fastest natural tick that arises from these ingredients. Now that does not mean there is a tiny physical clock sitting somewhere beneath the floorboards of the universe, dutifully ticking at Planck frequency like a nervous insect with impossible punctuality. Physics is rarely that literal, and the universe, to its credit, does not usually hide small clockwork devices inside its foundations. Planck frequency is better understood as a signpost. It points to a scale where our usual ideas about time, energy, quantum behaviour and gravity all begin to crowd into the same room. And when those ideas crowd together, the room becomes difficult to describe. Our best theories start stepping on each other's shoes. In ordinary life, frequency can rise without causing much philosophical trouble. A guitar string vibrates, a radio wave oscillates, visible light carries a far faster rhythm than sound, X-rays and gamma rays are faster still. We can keep climbing upward through the spectrum from gentle radio signals to light that can pass through flesh, to radiation born in violent cosmic events. Each step upward means the wave has more energy. A faster rhythm is not just a quicker rhythm. In quantum physics, it is tied to a more energetic packet of reality. This is why high-frequency radiation can be dangerous. It is not merely moving quickly in some decorative sense. It carries the ability to disturb atoms, break molecular bonds, and alter matter. So what happens if frequency keeps increasing? The energy associated with that rhythm becomes greater and greater. Eventually, if we push the idea far enough, the energy becomes so concentrated that gravity can no longer be ignored. This is important, because in everyday physics we often keep quantum mechanics and gravity in separate drawers. Quantum mechanics handles the very small, such as atoms and particles. Gravity handles the very large, such as planets, stars and galaxies. Most of the time, that separation works beautifully. An electron does not need Einstein's full theory of gravity to explain its behaviour in an atom, and a falling apple does not require a quantum field calculation to explain why it lands on the ground rather than politely hovering. But at the Planck scale, the drawers no longer stay separate. The small becomes so energetic that it also becomes gravitational. A wave with an impossibly high frequency would be associated with an enormous amount of energy packed into an extremely tiny region. And if enough energy is packed tightly enough, gravity responds. Not gently. It may respond by creating the conditions associated with a black hole. At that point, the attempt to make a frequency higher may defeat itself. You try to make a sharper tick, a smaller interval, a more concentrated burst of energy, and nature answers by hiding the result behind a gravitational boundary. It is a little like trying to look more closely at a secret by lighting a brighter lamp, only to discover that the lamp has become so intense it collapses the room around it. This is one reason Planck frequency is sometimes spoken of as a highest possible frequency. It is not highest in the same way a speed limit sign is high, with a traffic officer waiting nearby in a cosmic uniform. It is highest because beyond that scale, the physical meaning of frequency becomes unclear. Our language begins to slip. To speak of a wave, we need some meaningful idea of space and time through which that wave can vary. To speak of a tick, we need some meaningful idea of before and after. But if the time interval becomes smaller than the Planck time, we are no longer sure that our usual concept of time still applies. We may be asking nature for a distinction it does not make. This is where the topic becomes both fascinating and humbling. In school, time is often treated as if it is a perfectly smooth line. You can mark 1 second, then half a second, then half of that again, and keep going as long as your pencil remains sharp and your patience remains intact. Mathematically, this is easy. Physically, it may not be. There may be a level at which asking for a smaller interval is not wrong exactly, but meaningless, like asking what is north of the North Pole. The question sounds grammatical. It uses familiar words. But the place it points to may not exist in the way the question assumes. Planck frequency grows from this uncertainty. It is the inverse idea of Planck time, though we do not need formulas to understand the relationship. If Planck time is the smallest meaningful tick suggested by known constants, then Planck frequency is the fastest meaningful ticking rate suggested by those same constants. It is what you get when you imagine a clock that ticks once every Planck time. Such a clock would be so wildly fast that ordinary words begin to lose their grip. The rhythms of music would be glacial beside it. Atomic vibrations would seem slow. The fastest technological clocks humans have built would be nowhere close. Even light itself, which defines the maximum speed for signals moving through space, would cross only a Planck length during 1 Planck time. This does not mean we have measured Planck frequency directly. We have not placed a detector on a laboratory bench and watched it blink at the highest possible rate. The Planck scale is far beyond our current experimental reach. It sits in a realm where direct measurement becomes brutally difficult, not because scientists lack curiosity, but because the energies involved are so extreme and the distances and times are so tiny. Human instruments are remarkable. We can detect gravitational waves from merging black holes. We can measure time so accurately that tiny differences in altitude matter. We can study particles in accelerators and peer back toward the early universe through ancient light. But the Planck scale remains a frontier where our theories point more confidently than our instruments can travel, and that makes it a strange kind of scientific landmark. It is not imaginary, because it is built from real constants that appear throughout tested physics, but it is not fully understood, because the theory needed to describe it completely has not yet been finished. We have quantum mechanics, we have general relativity. Both are spectacularly successful in their own domains. But when we ask about the Planck scale, we are asking for the place where both must speak at once. So far, they do not share a common language. Their disagreement is not a small technical inconvenience. It is one of the deepest unresolved problems in physics. This is why the idea of the highest possible frequency is not simply a fact to memorize. It is a doorway into the unfinished part of science. It asks whether time is continuous or somehow granular. It asks whether space can be divided endlessly, or whether at some point the idea of distance changes. It asks whether black holes, quantum fields, and the earliest moments of the universe are all whispering about the same hidden structure. It asks whether the word possible means what we think it means when we stand near the edge of measurement itself. There is also a useful caution here. Popular explanations sometimes make the Planck scale sound like a hard floor made of tiny tiles, as though the universe were built from little cubes of space and little clicks of time. That picture may be tempting, but is not something we know for certain. Planck time may not be a literal smallest unit in the way a brick is a smallest part of a wall. It may instead be the scale at which our current theories stop being reliable. The difference matters. A map can end at the edge of known territory without the world ending there. The Planck scale might be the border of nature's discreteness, or it might be the border of our present understanding. Either way, it is important. Still, even as a border of understanding, it tells us something profound. It tells us that physics is not infinitely casual about extremes. When we push concepts too far, nature may change the rules. A smooth clock, a simple wave, a clean measurement, a neat location in space. These are ideas that work wonderfully in familiar conditions. They let us build radios, lasers, satellites, computers, and telescopes. But at the Planck scale, the familiar furniture of reality may not stay still. Space may fluctuate. Time may lose its usual order. Gravity may behave quantum mechanically. The clean stage on which events happened may become part of the performance. This is not a reason to feel lost. It is a reason to feel carefully curious. Every major advance in physics has involved discovering that a familiar idea was only part of the story. Earth feels still, but it spins and orbits. Matter feels solid, but it is mostly structured emptiness held together by fields and forces. Time feels universal, but relativity showed that it depends on motion and gravity. The Planck frequency belongs to this tradition. It takes an everyday idea, the rhythm of something repeating, and follows it until it becomes a question about the limits of reality. Imagine, in a very ordinary way, tapping your finger once on a table. Then imagine tapping faster, faster still. Soon the taps blur into a buzz, faster again, and the table is no longer the right object for the thought. Move from fingers to machines, from machines to atoms, from atoms to light, from light to the most energetic events in the cosmos. Keep increasing the rhythm in your mind. At each step, the question changes. At first, it is about motion. Then it is about vibration. Then it is about radiation. Then it's about energy. Then finally it becomes about gravity and the nature of time itself. That is the path we're taking tonight. Not a race toward a number, but a slow walk toward why that number matters. The phrase highest frequency possible can sound like the universe is presenting us with a final note, a tone so high that nothing can sing above it. But we should be careful with the metaphor, because this is not a sound in the ordinary sense. It is not something ears could hear, even in principle. Sound needs a medium, such as air or water or solid matter, and it belongs to the motion of particles pushing and pulling against one another. Planck frequency is much more general. It is about the fastest meaningful rate at which physical change could be described if our current understanding is pointing in the right direction. It is less like a note, and more like the edge of what a note could mean. There is something quietly comforting about that, at least to me. We live in a world that often feels rushed. Messages arrive instantly. Screens refresh. Machines process. Markets react. Clocks glow from every wall and pocket, and the day can feel chopped into smaller and smaller demands. Yet physics tells us that speed itself may have a boundary of meaning. There may be a deepest rhythm below the noise, not a rhythm we can use to schedule breakfast, but one that reminds us that even the universe has limits to how finely it can be asked to divide itself. Reality may not be an endless blur of smaller and faster. It may have thresholds, regions where the old questions stop working and new ones have to be invented. And so, as we begin, the Planck frequency is not just a giant number hiding in a textbook. It is a meeting point. It brings together the smallest time we can meaningfully discuss with the greatest rate of change we can meaningfully imagine. It marks the place where frequency becomes energy, energy becomes gravity, and gravity begins to bend the very stage on which frequency was supposed to happen. It stands near the unfinished bridge between quantum theory and the geometry of space and time. It is a reminder that the universe is understandable, but not always in the way we first expect. For tonight, we will not force the idea too quickly. We will let it unfold from familiar rhythms toward unfamiliar scales. We will begin with clocks, but not the kind hanging on a wall. We will think about the hidden clocks inside nature, the steady patterns that allow atoms to glow, light to travel, and particles to behave. Then we will approach Planck time, that astonishingly tiny interval that gives Planck frequency its meaning. From there, we will turn the idea around and ask what it means for a rhythm to be the fastest possible. We will look at why shorter waves demand greater energy, why too much energy in too little space invites gravity into the conversation, and why the universe may protect itself from being measured beyond a certain point. For now, the important thing is simply to hold the central question gently. Not what number is Planck frequency, not how many cycles fit inside a second. Those are useful details, but they are not the heart of the story. The deeper question is what happens when frequency is pushed to the limit of physical meaning? What happens when a tick becomes so brief that time itself is no longer a quiet background, but part of the mystery being examined? What happens when the fastest possible rhythm leads us not to a louder universe, but to a stranger and quieter one, somewhere far below ordinary clocks, below the pulse of light in a laboratory, below the vibrations of atoms and the flicker of particles? Physics has placed a marker. It does not say stop in the ordinary sense, it says be careful. Past this point, the concepts you brought with you may not survive unchanged. A second may no longer be something you can simply divide. A wave may no longer be something you can simply sharpen. A measurement may no longer be something you can simply improve by adding more energy. The universe, at its deepest scales, may not be hiding because it is distant. It may be hiding because our usual ways of asking questions become too heavy, too sharp, too disruptive. And that is where the story truly begins, with the idea of a clock so small and so fast that it cannot be built, held or watched, yet still teaches us something about the foundations of everything. Not a clock made of gears or quartz or atoms in a laboratory, but a limit suggested by the constants of nature themselves. A tiny clock hidden not in space, but in the rules that make space and time possible. That tiny clock hidden beneath reality is not the sort of clock anyone could place on a desk. It has no hands, no face, no gears, and no polite little tick that a sleepy listener could count in the dark. It is not hidden under a floorboard of space, waiting for some future physicist with a very small screwdriver. The phrase is a way of speaking about something stranger and more careful. It points to a natural limit suggested by the deepest constants we know, a limit where the ordinary meaning of time begins to change. When we talk about the Planck scale, we're not talking about a miniature object tucked away inside matter. We're talking about the point where our best ideas about clocks, distance, energy, and gravity all begin to press against one another. A normal clock is useful because something inside it repeats. In an old clock, a pendulum swings. In a wristwatch, a tiny crystal vibrates. In an atomic clock, atoms shift between states with incredible regularity. Each of these clocks depends on a repeating process that can be counted. The better the process repeats, the better the clock. This is how humans learn to measure time more and more precisely. We move from shadows to flowing water, from gears to pendulums, from quartz to atoms. Each improvement gave us a steadier rhythm, a more dependable way to say that this moment is separated from that moment by a certain amount of time. But every clock, no matter how advanced, must be made from physical things. It must use energy. It must occupy space. It must interact with the rest of the universe in some way. This is easy to forget because clocks can feel almost magical when they are precise. A modern atomic clock can keep time with such accuracy that ordinary human life seems far too untidy to deserve it. You could miss a bus, burn your toast, and forget where you put your keys while the clock continues calmly measuring time with no sympathy at all. Yet even that clock is still a physical machine. It is built from atoms and fields. It depends on signals, measurements, and the behavior of matter. It is not outside nature. It is nature, arranged carefully enough to count itself. The Planck scale asks what happens when we imagine the most extreme clock possible. Not merely a better clock than the ones we have built, but a clock pushed toward the deepest boundary that known physics can describe. To measure a shorter interval of time, you need a faster process. A slow clock cannot measure quick events. If you want to time a sprinter, you need something more precise than a sundial. If you want to measure the flicker of a laser pulse, you need something far beyond a kitchen timer. This pattern continues as we move into smaller and smaller intervals. To measure a tiny slice of time, the clock must involve faster changes, and faster changes require higher energies. At first, that seems like a simple engineering problem. Build better instruments. Use stronger lasers. Use colder atoms. Use cleaner laboratories. That is how much of experimental physics has advanced, with patience, cleverness, and machinery that looks as if it was assembled by people who enjoy both mathematics and extremely organised wiring. But the Planck scale is different. It is not merely difficult because our tools are clumsy. It is difficult because the tool itself begins to disturb what it tries to measure. The act of making a clock fast enough to probe such a tiny interval would require concentrating so much energy into so small a region that gravity could no longer be treated as a minor detail. This is one of the central ideas behind the tiny clock beneath reality. It is not that there is a proven smallest tick that the universe must obey like a law written on a classroom wall. It is that if you try to make time measurements finer and finer, you eventually reach a place where the measurement would demand conditions so extreme that space and time themselves may no longer behave in the ordinary way. The clock would not simply sit inside time, measuring it from a safe distance. The clock would affect the structure of time around it. It would become part of the problem. This is a very different picture from everyday life. When you look at a clock on the wall, you do not worry that the clock is bending the room or changing the flow of time in a noticeable way. Its gravity is far too weak, its energy far too small, its presence far too ordinary. Even a laboratory atomic clock, magnificent as it is, does not threaten to collapse into a black hole or tear the fabric of space. It simply measures. But a clock capable of resolving intervals near the Planck time would be associated with such extreme energy that the neat separation between observer, instrument, and event would start to fail. The clock would no longer be a quiet witness, it would be an active participant in the geometry of reality. To understand why this matters, it helps to think about what a clock really does. A clock does not create time. It does not pour time into the world the way a tap pours water into a sink. A clock compares change with change. It says that while one thing happened, this other repeating thing completed a certain number of cycles. Time measurement is always a comparison. The clock gives us a stable pattern, and we use that pattern to describe other patterns. The day is compared with the turning of Earth. A second is compared with the behaviour of atoms. A heartbeat is compared with the rhythm of a body. Even when we speak casually about time passing, what we actually observe is change. This is why the idea of the smallest meaningful clock is so powerful. If time is measured through change, then the fastest meaningful clock would require the fastest meaningful change. The Planck frequency is connected to this idea. It represents the rate of ticking that corresponds to the Planck time. Imagine, not as a real device but as a thought experiment, a clock that completes one tick in that tiny interval. It would not be like any clock we know. Its rhythm would be so fast that even the most energetic processes we commonly study would seem slow by comparison. It would mark a boundary where the ordinary language of ticking begins to turn into questions about the structure of time itself. Max Planck did not introduce his famous scale by building such a clock. He was working on the problem of radiation from heated objects, a subject that may sound less dramatic than the edge of reality, but turned out to be one of the most important doorways in science. His work helped reveal that energy at microscopic scales behaves in discrete portions. This did not mean that every part of nature was obviously made of little pieces in a simple way. It meant that the old assumption of perfectly smooth energy exchange was not always correct. Nature had a new rule hidden inside it, and that rule eventually helped form quantum theory. From the constants connected with quantum behaviour, light, and gravity, physicists can construct natural units. These units are not based on human convenience. A meter is human-chosen. An hour is tied to Earth and tradition. But the Planck units come from constants that appear to describe the universe at a basic level. That is what makes them feel so serious. They are not merely small or large because we chose to define them that way. They arise when nature's own constants are combined. The Planck time is one of these units. The Planck frequency is the corresponding idea of a rate so fast that it matches that tiny interval. Still, we should keep our feet on the ground, even while discussing scales that make the ground seem enormous. Planck time is not known with certainty to be a literal smallest unit of time. Many explanations say it that way because it is memorable, and because it gives the imagination something firm to hold. But the honest scientific statement is more careful. Planck time is the scale at which we expect quantum effects of gravity to become important. It is the scale where our current theories stop giving clear answers if we try to use them together. It may turn out that time is granular there. It may turn out that time remains continuous, but behaves in a way we do not yet understand. It may turn out that time emerges from something deeper that does not resemble time at all. The Planck scale tells us where to look for the mystery, not exactly what we will find. This careful distinction matters because physics is not only a collection of grand claims, it is also a discipline of knowing how much we know. There is a kind of intellectual comfort in pretending that every difficult question already has a clean answer. But real science often lives in the space between confidence and uncertainty. We can say with confidence that the Planck scale is built from fundamental constants. We can say with confidence that our present theories point to it as an extreme boundary. We can say with confidence that quantum mechanics and gravity must both matter there. But we cannot yet say exactly what time is doing at that scale. The tiny clock is not a solved machine. It is a sign that the machine of understanding still has missing parts. When people first hear about the Planck scale, they often imagine zooming inward through matter. First a hand, then skin, then cells, then molecules, then atoms, then nuclei, then smaller and smaller structures. This mental journey is useful, but it can also mislead. The Planck scale is not simply the next small thing after particles, like another layer hidden below the last one. It is not necessarily a tiny bead at the bottom of matter. It is a scale of length, time, energy, and gravity where our concepts begin to lose their ordinary independence. We are not just looking for smaller pieces. We're asking whether the ideas of piece, place, interval, and measurement remain valid. A clock at this scale would have to ask time to define itself with almost impossible sharpness. Yet quantum mechanics tells us that the sharper we try to make certain descriptions, the more other aspects become uncertain. This is not because our instruments are bad. It is built into the behavior of quantum systems. At small scales, nature does not always provide the kind of definite properties that our everyday minds expect. Particles do not behave like tiny billiard balls with exact positions and speeds waiting patiently to be discovered. They behave according to probabilities, fields, and measurements that cannot be separated from the act of observation as neatly as classical physics hoped. Gravity adds another complication. In Einstein's picture, gravity is not simply a force pulling things together. It is connected to the shape of space and time. Matter and energy influence that shape, and the shape influences how matter and energy move. This idea works beautifully for planets, stars, galaxies, and black holes. But at the Planck scale, if energy becomes concentrated into an extremely tiny region, the shape of space and time may fluctuate in a quantum way. The background on which the clock is supposed to tick may not be a smooth background anymore. It may be restless, uncertain, and difficult to define. Some physicists have used the phrase quantum foam to describe this possible behavior. The phrase is vivid, but we should handle it gently. It does not mean space is literally made of bubbles like soap in a sink. It means that at extremely small scales, the geometry of space and time might fluctuate wildly, rather than remaining smooth. If that picture is even partly right, then the tiny clock hidden beneath reality would not tick in a quiet, empty room. It would be trying to tick in a room whose walls, floor and ceiling are not fully settled. Before and after might still exist in some deeper sense, but perhaps not in the simple order we're used to. This is why Planck frequency is such a powerful idea for a sleep science story. It sounds at first like a question about speed. What is the fastest possible vibration? But it becomes a question about trust. How far can we trust our usual concepts? How far can we stretch the word clock before it stops meaning what it means in ordinary life? A clock requires a stable process. A stable process requires a world in which change can be tracked. Change requires some way to distinguish one state from another. At the Planck scale, each of those requirements becomes difficult. It is as if physics has followed the ticking sound downward and found not a final gear, but a fogged mirror. Even so, the journey is not empty. Limits in physics are often more informative than ordinary facts. The speed of light is a limit, and because of it, we learned that space and time are linked. Absolute zero is a limit, and because of it, we learned deep lessons about heat, motion, and quantum states. The Planck scale may be another such limit, not just a barrier, but a clue. It may be telling us that time is not a passive container. It may be telling us that measurement has a cost. It may be telling us that the universe cannot be understood by separating the smallest things from the largest structures, because at the deepest level, the small and the gravitational become one problem. There is a quiet irony here. The smallest clock we can imagine leads us to some of the biggest questions. It asks about the beginning of the universe, because the early universe may have passed through conditions where Planck scale physics mattered. It asks about black holes, because black holes bring gravity, quantum effects, and extreme concentration together. It asks about information, because a clock is a device that records order, and the universe seems to preserve and transform information in ways we are still trying to understand. It asks about causality, because a clock is meaningful only if events can be arranged in a before and after relationship. Follow the tiniest tick far enough, and suddenly you're standing beside the largest unfinished puzzles in science. The reason this happens is that time is not an isolated idea. We often treat it that way because clocks make it look simple. A clock on a wall seems to measure one thing, time, while everything else happens around it. But in modern physics, time is woven into motion, energy, fields, gravity, and information. Change the conditions enough and time changes too. Move very fast and time is measured differently. Stand in stronger gravity and time passes differently compared with somewhere farther away. Shrink the interval toward the Planck scale and time may no longer be described independently of quantum gravity. The tiny clock is hidden beneath reality, because time itself may be part of reality's construction, not just a label pasted on afterward. Our bodies have clocks too, though they belong to a much gentler scale, a heartbeat, a breath, the daily rhythm of sleep and waking, the slow chemical cycles inside cells. These are not Planck clocks, they are soft biological clocks, built by evolution under sunlight and darkness, yet they help us feel why clocks matter. A living being needs rhythm. Without rhythm, there is no coordination, no memory of sequence, no expectation, no sense that one thing follows another. Physics uses clocks to measure events. Life uses clocks to survive events. The Planck scale sits far below biology, but the basic need for order is shared. To understand anything, we need some way to say this changed and then this changed after it. The tiny clock at the bottom of the story is therefore not just about speed, it is about the possibility of ordering change at all. If a clock ticks too slowly, it misses details. If it could tick infinitely fast, perhaps it could capture everything. But physics suggests that infinite sharpness may not be available. To capture ever finer details, a clock must use ever greater energy. At some point, that energy changes the thing being measured. At some point, the clock becomes so powerful that it can no longer be treated as a harmless observer. It is a gentle lesson with a severe conclusion. Nature may not permit a view from nowhere. Every measurement belongs to the universe it measures. This is very different from the old dream of perfect knowledge. Classical physics often encourage the idea that, given enough information, the universe could be predicted like a machine. In that view, a perfect clock and perfect measurements might reveal the whole future and past. Quantum theory softened that confidence. Relativity changed the meaning of time itself. The Planck scale takes us further, suggesting that at the deepest levels, the machinery of prediction may depend on structures we do not yet understand. The universe may not be a clockwork mechanism with smaller and smaller gears. It may be something for which clockwork is only a useful surface description. That does not make clocks unimportant. Quite the opposite. The history of physics is deeply tied to better timekeeping. Accurate clocks allowed navigation across oceans. Atomic clocks allow global positioning systems to work. Precise timing lets us test relativity, coordinate communications, and study particles. Every improvement in timekeeping has opened a new way to understand nature, but the Planck frequency reminds us that this progress may have a conceptual edge. There may be a place where making clock faster no longer gives clearer time, because time itself is no longer the simple thing the clock was designed to measure. It is worth noticing how strange this is. Usually, more precision means less mystery. A blurry photograph becomes clear when the lens improves. A rough measurement becomes exact when the instrument improves. But at the Planck scale, more precision may produce more mystery. Trying to focus more sharply on time may reveal that time is not a smooth background waiting to be photographed. It may be dynamic, quantum, and tied to gravity. The closer we look, the less the old picture behaves. This does not mean the universe is irrational. It means our familiar categories were shaped by familiar scales. They work well where we live, among tables, lamps, planets, and stars. They may not survive unchanged at the scale where time itself becomes part of the experiment. So the tiny clock hidden beneath reality is best understood as a boundary in our thinking. It says that if we follow the idea of time measurement down to its deepest known scale, we arrive at a place where a clock cannot be imagined without quantum mechanics, cannot be understood without gravity, and cannot be separated cleanly from the thing it measures. It is not a clock you can hear. It is not a rhythm you can feel. It is not a machine waiting in the dark. It is a natural limit that tells us our ordinary world, with all its clocks and calendars, may rest on a foundation where time is far less ordinary than it seems, and perhaps that is enough for now. Not an ending, but a settling of the idea. We began with the thought of a hidden clock, and it has already led us away from gears and ticking hands toward the deep connection between measurement and reality. Beneath every ordinary clock is a physical process. Beneath the best atomic clock is quantum behavior. Beneath the idea of the fastest possible clock is the Planck time, and beneath that, or perhaps around it, lies the unfinished question that keeps physicists awake in a very different way from a noisy alarm. What does time become when the universe is examined at the smallest meaningful scale? To understand what Planck time really means, it helps to begin with a very ordinary idea and then follow it carefully until it becomes extraordinary. Think of a second. Not as a number on a screen, but as an experience. A second is long enough for a blink, a short breath, the click of a switch, the soft tap of a finger on a table. It feels small but still human. You can notice it. You can wait through it. You can count several of them in your head without much trouble, though your counting may wander slightly if you are tired, distracted, or listening to a very calm voice talking about physics late at night. Now, imagine cutting that second into smaller pieces. Half a second is still easy to feel. A tenth of a second is quick, but your nervous system can still react to it in some situations. A thousandth of a second is already slipping away from ordinary awareness, though cameras, electronics, and scientific instruments can work at that scale. Keep going smaller, a millionth of a second, a billionth of a second, a trillionth of a second. Each time the interval becomes less like a moment you can feel, and more like a technical fact. It is still time, but it has left the living room and entered the laboratory. Physicists do this all the time. They measure processes that are far too quick for human senses. Molecules rotate and vibrate. Electrons shift states. Light pulses can be made extremely brief. Particles can appear, transform, and vanish in intervals so small that ordinary language starts to feel bulky beside them. But even these incredibly short times are still far, far larger than Planck time. Planck time is not merely small in the way a speck of dust is small compared with a house. It is small in a way that puts it near the edge of what our current physics can describe at all. A useful way to approach it is through light. Light is the fastest messenger in the universe, at least according to everything we know from relativity. It does not stroll, it does not hesitate. In empty space, it moves at the maximum speed that information, cause, and effect appear to be allowed to travel. During one ordinary second, light can circle Earth several times. During a tiny fraction of a second, light still crosses distances that matter to technology and experiments. But during one Planck time, light would travel only about one Planck length. That pairing is important. Planck time is connected to Planck length in the same way a travel time is connected to a travel distance. It is the time light would need to cross the smallest natural length scale suggested by the combination of quantum theory, gravity, and relativity. That explanation is careful because it avoids saying too much. It is tempting to say that Planck time is the smallest possible unit of time. Many popular explanations say exactly that. It is memorable, and it gives the mind a clear image, as if time were made of tiny beads, and Planck time were the smallest bead. But physicists are often more cautious. Planck time is not proven to be the smallest actual piece of time. It is the scale at which our current theories tell us that something very important must happen. It is where the smooth time of relativity and the uncertain behaviour of quantum physics can no longer be comfortably kept apart. This distinction may sound subtle, but it changes the entire meaning. If someone says Planck time is definitely the smallest tick of the universe, that sounds like a finished answer. If someone says Planck time is the scale where our known laws point toward quantum gravity, that sounds like an open doorway. Science prefers the second statement, because it is more honest. We do not yet know whether time is made of discrete pieces, like frames in a film, or whether time remains continuous all the way down, or whether time is not fundamental at all but emerges from something deeper. Planck time does not settle that debate by itself. It tells us where the debate becomes unavoidable. The reason Planck time matters comes from the ingredients used to define it. It is built from constants that sit at the foundations of modern physics. One ingredient comes from quantum theory, which governs the small and tells us that energy and measurement do not behave the way everyday objects suggest. Another ingredient comes from gravity, which governs the attraction of mass and energy, and, in Einstein's theory, the shaping of space and time. Another ingredient is the speed of a light, which links space and time and sets the cosmic speed limit. When these ingredients are combined, they produce a timescale that seems to belong not to any human clock, planet, or atom, but to nature's own structure. This is why Planck time feels different from a second, an hour, or a day. A day comes from Earth turning. An hour comes from human division of the day. A second, as used today, is tied to the behaviour of atoms, but its historical roots still come from human timekeeping. Planck time is not chosen because it is convenient. No one would choose it for convenience. It is so small that it is practically unusable for everyday measurement. You will never set a kitchen timer in Planck times, unless the kitchen has become very strange indeed. Instead, Planck time arises because the constants of nature, when placed together, point toward it. That makes it a natural unit. Natural units are not necessarily easy units. They are not designed to make shopping, cooking, or catching trains simpler. They are designed to reveal how nature scales itself when human preferences are removed. In that sense, Planck time is like a message from the basic architecture of physics. It says that if quantum effects, gravity and light all matter at once, this is the kind of time interval that appears. Not because humans find it comfortable, but because the universe's constants lead there. To see why this is so important, imagine trying to measure an event that happens in an extremely short time. To do that, you need something that changes even faster. A clock can only resolve an interval if its own internal rhythm is fine enough. A slow pendulum cannot measure the flash of a particle collision. A wristwatch cannot time the movement of electrons. As the interval becomes smaller, the clock must become more energetic, more precise, and more tightly focused. At ordinary scales, this is challenging but possible. At extreme scales, it becomes dangerous for the concept itself. Quantum mechanics tells us that measuring very small things requires interacting with them. You cannot simply look without consequences. To probe a smaller region of space or a shorter interval of time, you generally need higher energy. But energy is not innocent. In relativity, energy contributes to gravity. If you concentrate enough energy into a small enough region, gravity becomes strong. Push this too far, and the region may behave like a black hole, hiding what you are trying to inspect. So the attempt to measure time more sharply can run into a physical obstruction. The sharper your probe, the more it may disturb the very fabric you wanted to examine. Planck time sits near the place where this obstruction becomes central. Below that scale, our usual idea of measurement may no longer work. It may not be meaningful to say that one event happened a smaller interval after another if the structure of space and time itself is fluctuating or undefined. This is not just a practical problem, like needing a better microscope. It may be a conceptual problem, like asking for a colour beyond all possible vision, or asking a ruler to measure itself after it has melted. The words still seem familiar, but the situation no longer supports the old meaning. This is where Planck time becomes more than a small number. It becomes a warning label on the edge of known physics. It tells us not to assume that time can be divided forever, just because mathematics allows endless division. Mathematics is a language of great power, but physical reality does not always obey every image mathematics can describe. We can imagine a second cut into endless smaller intervals, but nature may not provide physically meaningful distinctions all the way down, or it may provide them in a way very different from our current picture. There is an old habit in human thinking to believe that if something exists, it must be made of smaller things. A wall is made of bricks. Bricks are made of grains and minerals. Minerals are made of atoms. Atoms are made of smaller particles and fields. So perhaps we imagine time must be made of smaller timepieces. Maybe Planck time is one of those pieces. This picture is simple, and it might even contain part of the truth. Some approaches to quantum gravity do suggest that space or time may have a granular structure, but the matter is not settled. Other approaches treat the Planck scale differently. They may suggest that geometry becomes quantum, or that time emerges from relationships, or that the familiar idea of a ticking sequence is not fundamental. So when we ask what Planck time really means, the answer is not simply that it is the smallest tick. The better answer is that Planck time is the interval at which the known languages of physics begin to overlap and interfere. Quantum mechanics, relativity, and gravity all have something to say, but we do not yet have one complete theory that lets them speak together clearly. Planck time marks the region where that missing theory is needed. This is why it often appears in discussions of the very early universe. If we run the history of the cosmos backward, the universe becomes hotter, denser, and more extreme. At some very early stage, our current theories become unreliable. We can describe much of cosmic history with impressive confidence, but near the beginning, close to the Planck time after what we call the Big Bang, the conditions are so extreme that quantum gravity should matter. It is not honest to pretend we can describe that first instant with the same confidence we use for later cosmic events. Planck time stands like a fog bank at the earliest edge of the map. We know something lies beyond our current description, but the details are not yet visible. That fog bank does not mean ignorance in a hopeless sense. It means a frontier. In science, frontiers are valuable because they tell us where new ideas are needed. The Planck time is one of the most important frontiers because it is not tied to one small puzzle. It is tied to the relationship between the two great pillars of modern physics. Quantum theory has been tested with stunning success. General relativity has also been tested with stunning success, yet they are built in very different ways. Quantum theory usually works against a background of time, treating time as something that flows while quantum states change. General relativity treats space and time as dynamic, shaped by matter and energy. At the Planck scale, neither view can simply ignore the other. This creates the famous problem of quantum gravity. We need a theory that can describe gravity according to quantum principles, or perhaps a deeper theory from which both quantum mechanics and gravity emerge. No one knows for sure what the final answer will look like. There are serious ideas, such as string theory, loop quantum gravity, causal sets, and other approaches, each with its own mathematical structure and physical hopes. Some suggest tiny vibrating structures. Some suggest networks of relationships. Some suggest that space and time themselves may be built from more basic information. The details differ, but they all take the Planck scale seriously, because that is where the ordinary smooth picture is expected to break. For a sleepy mind, this might sound like the beginning of a headache, but it can also be made gentler. Imagine a map of a coastline. From far above, the coastline looks smooth. Fly lower, and you see bays, cliffs, rocks, and curves. Walk along it, and the line between land and water becomes even more complicated. At some point, the idea of a single, clean coastline depends on the scale at which you measure. Space and time may be similar in a deep way. At everyday scales, time looks smooth and reliable. At atomic scales, it still functions well enough for quantum theory. At the Planck scale, the smooth line may no longer be the right description. This does not mean time becomes chaotic in any ordinary sense. It means we should be careful about importing everyday intuition too far downward. Everyday time is shaped by memory, clocks, motion, and change. Relativistic time is shaped by speed and gravity. Quantum time is involved in the evolution of probabilities. Planck time asks whether all these meanings can be traced to something deeper. It is like following a river upstream until the river becomes small streams, then wet ground, then mist. At some point the word river still helps, but only if we remember that the form has changed. Another common misunderstanding is that nothing can happen in less than a Planck time. That may be true in some future theory, but we do not know it yet. The safer statement is that our current understanding cannot reliably describe physically meaningful processes below that scale. There is a difference between saying something is forbidden and saying our concepts no longer apply. A child might say there is nothing beyond the horizon because they cannot see past it. An explorer says the horizon marks the limit of view, not the limit of the world. Planck time is more like the explorer's horizon. It marks the edge of our current view. This is especially important when people ask whether Planck time is like a frame rate for the universe. The image is appealing. A movie appears smooth because it is made from still frames shown quickly. Maybe the universe updates itself every Planck time. Maybe reality is like a cosmic film or a simulation refreshing at an unimaginable speed. It is a fun idea, and it appears often in science fiction and casual conversation. But physics does not currently say this is true. Planck time is not known to be the refresh rate of the universe. It is a scale derived from constants, not direct evidence that reality blinks from one frame to the next. Still, the frame idea is useful as long as we treat it as a metaphor and not a fact. It helps us imagine why a smallest meaningful interval would change how we think about motion and causality. If time had a smallest unit, then motion might not be infinitely smooth. Change might happen in steps. But if time is continuous, the Planck scale may instead signal that the geometry of time becomes uncertain or quantum. If time is emergent, then Planck time may be related to the conditions under which the familiar experience of time appears from deeper relationships. Each possibility is fascinating, but none should be presented as settled. The Planck time also reminds us that smallness and power can be linked. In ordinary life, tiny things seem weak. A grain of dust is easy to ignore. A small sound disappears in a large room. But in physics, extreme smallness can involve enormous energy. To confine something to a smaller region, or to probe a shorter interval, energy rises. At the Planck scale, that energy is so significant that gravity becomes strong even though the region is tiny. This is one of the great surprises of the subject. The smallest scale does not lead away from gravity. It leads directly into it. That is why black holes keep appearing in the conversation. A black hole is not just a large collapsed star. More generally, it is what happens when energy or mass is packed so tightly that a boundary forms beyond which light cannot escape. If an attempt to measure an ultra-tiny interval requires concentrating enough energy in a small enough region, the measurement may create something like a tiny black hole. This possibility suggests a kind of natural protection against infinite measurement. The universe may not allow us to observe arbitrarily small intervals, because the effort to do so changes the situation completely. This connects Planck time with the limits of knowledge, but not in a gloomy way. Physics has always advanced by discovering limits. The speed of light limited old ideas of motion and gave us relativity. Quantum uncertainty limited old ideas of measurement and gave us a deeper theory of matter. The Planck scale may limit old ideas of space and time and point toward the next theory. A limit is not only a wall, sometimes it is the outline of a door. There is also a philosophical calm in realizing that Planck time is not competing with ordinary time. It does not make your morning coffee less real, or your memories less meaningful, or the clock beside your bed less useful. Different levels of description can be true at once. A table is solid in daily life, even though at the atomic level it is mostly empty space structured by forces. Air is smooth to your hand, even though it is made of countless molecules. Temperature is real, even though it emerges from microscopic motion. In the same way, ordinary time may be real at our scale, even if its deepest origin is stranger than we know. So Planck time really means several things at once, depending on how carefully we speak. It is a natural timescale built from constants that belong to quantum theory, gravity, and relativity. It is the time light would take to cross the Planck length. It is the scale where quantum gravity is expected to become important. It is not proven to be the smallest possible piece of time, but it may be near the boundary where the question of smaller pieces becomes physically unclear. It is a marker of humility, showing us where our best theories become incomplete, and it is a guidepost, pointing future physics toward the place where the smooth fabric of space and time may reveal its deeper texture. This is why Planck time is so often described with awe, even by scientists who are careful with their words, not because it is magical, not because it proves the universe is digital or simulated or made of tiny clock ticks. It deserves awe, because it is where measurement, energy, gravity and time meet in their most extreme form. It is the point where the tools that have served us so well begin to tremble. A second can be counted, a millisecond can be measured, an atomic transition can be tracked with extraordinary precision. But Planck time asks a harder question. What does it mean to measure time when the act of measurement may disturb space and time themselves? In the quiet of this thought, the ordinary world returns looking slightly different. A clock ticking on a wall is no longer just a household object. It is the top layer of a very deep story. Beneath its rhythm are atoms. Beneath atoms are quantum fields. Beneath quantum fields, perhaps, is some unknown structure where time is not yet the familiar river of daily experience. The Planck time is not a place we can visit, but it is a scale our theories cannot ignore. It is a reminder that every ordinary second contains depth so small that even imagination has to slow down to approach them. And once that idea settles, the path toward Planck frequency becomes more natural. If Planck time is the tiniest meaningful interval suggested by the constants of nature, then the fastest meaningful rhythm would be the rhythm that fits one tick into that interval. To understand the highest possible frequency, we first had to understand the timescale it comes from. Not as a final answer, not as a tiny stopwatch at the bottom of the world, but as the point where time stops being merely what clocks measure and becomes part of the deepest question physics is still trying to ask. Planck time gives us the tiniest meaningful interval suggested by the constants of nature, but Planck frequency asks us to turn that thought around. Instead of asking how brief a moment can be before our current physics becomes uncertain, we ask how many such moments could fit inside one ordinary second. That sounds like a simple reversal, almost like turning an hourglass upside down and watching the sand fall the other way. But in physics, reversing a question can change its personality completely. A tiny time interval becomes an enormous rhythm, a smallness becomes a largeness, a limit at the bottom of measurement becomes a limit at the top of vibration. Frequency is the language of repeated change. If something moves back and forth once in a second, it has a slow rhythm. If it moves many times in a second, it has a faster rhythm. A pendulum in a grandfather clock swings with calm dignity. A guitar string vibrates much faster. The air around a speaker trembles quickly enough to become sound. Visible light vibrates at a rate so high that our ears cannot hear it, and our fingers cannot feel it, yet our eyes can detect its effects as colour. Gamma rays, born in nuclear events and violent cosmic places, have still higher frequencies, and with that higher frequency comes greater energy. This connection between frequency and energy is one of the essential steps toward understanding why Planck frequency is not merely a large number, but a boundary where the idea of a wave begins to approach the edge of known physics. In daily life, we usually think of time and frequency as separate ideas. Time is what clocks measure. Frequency is what describes music, radio, light, or the buzz of a machine in the next room. But they are secretly two ways of looking at the same pattern. A slow repeating process takes a long time to complete each cycle. A fast repeating process takes a short time. If the time for one cycle becomes smaller, the frequency becomes larger. If the time for one cycle becomes enormous, the frequency becomes tiny. The two ideas lean against each other. One describes the length of a single repetition. The other describes how many repetitions occur in a given span. That is why Planck frequency comes naturally from Planck time. Imagine a clock that ticks once every Planck time. Not a real clock, because no known material device could do this, and no laboratory could simply place such a clock on a table. But as a thought experiment, it is useful. If one tick takes one Planck time, then the number of ticks that would fit into one ordinary second is the Planck frequency. This is the fastest natural ticking rate suggested by the same constants that define Planck time. It is time turned upside down, not in the sense that time reverses, but in the sense that the smallest interval becomes the greatest rate. At first, this may sound like a trick of definitions. If Planck time is very small, then of course the corresponding frequency is very large. But the physical meaning is much deeper. A high frequency is not just fast motion. In quantum physics, higher frequency is tied to higher energy. This is why the colour of light matters. Red light has a lower frequency than blue light, and blue light carries more energy per tiny packet of light than red light. Ultraviolet light has still more. X-rays and gamma rays have more again. As frequency climbs, the wave does not simply become more hurried, it becomes more capable of affecting matter. This is why Planck frequency is not like asking for the fastest drummer in the universe, amusing as that image might be. It is asking what happens when a wave has so high a frequency that the energy associated with it becomes extreme enough for gravity to matter. At ordinary frequencies, gravity is irrelevant. A radio wave passing through your room does not bend space-time in any useful way. A beam of visible light has energy, but not enough in ordinary conditions to make gravity part of the discussion. Even very energetic radiation can usually be studied through quantum theory, without needing to worry that it will reshape the geometry of space around itself in a dramatic manner. But as frequency rises toward the Planck scale, that comfortable separation disappears. The Planck frequency belongs to the realm where a wave would be associated with a concentration of energy so immense that gravity could no longer stand quietly in the background. Gravity would enter the conversation not as a small correction, but as a central character. That is one of the reasons it may represent a highest meaningful frequency. If we tried to imagine a wave with a frequency higher than the Planck frequency, we would be imagining something with an even shorter cycle than Planck time and an even greater associated energy. At that point, the attempt to describe it as an ordinary wave moving through ordinary space-time may no longer make sense. The stage on which the wave is supposed to oscillate may itself become unstable, uncertain, or dominated by quantum gravitational effects. There is a useful way to picture the difference between ordinary high frequency and Planck frequency. Think of zooming in on a sound wave. At first you can see smooth rises and falls. Zoom in further and the wave still has shape. Now move from sound to light. The wave is no longer something you can watch directly, but mathematics and instruments reveal its rhythmic behavior. Move to higher and higher energy radiation, and the wavelength becomes shorter, the frequency faster, the energy greater. Continue the climb in imagination, and eventually you reach a point where the wavelength associated with that energy is close to the Planck length, and the time for one cycle is close to the Planck time. This is not simply a smaller ripple. It is a ripple so compressed that its own energy may threaten the smooth background it needs in order to be called a ripple at all. That may be the most important sentence to hold gently. At Planck frequency, the wave may disturb the very space-time it requires for its definition. In ordinary physics, we often place a wave in space and let it evolve in time. We imagine space and time as a stage while the wave is the performer, but at the Planck scale, the performer becomes so energetic that the stage cannot be ignored. The stage bends, responds, fluctuates, perhaps even loses the smoothness we assumed. A wave of such frequency would not merely occupy space-time, it would be deeply entangled with the structure of space-time. This is why Planck frequency is sometimes treated as a limit of physical meaning, rather than a practical frequency we could detect. We cannot build an antenna for it. We cannot tune a radio to it. We cannot listen for it in the way we listen for a signal from a distant spacecraft. It is not a hidden station broadcasting beneath reality. It is a scale that emerges when we ask how fast a rhythm can be before our current concepts break down. The word frequency remains useful up to a point, but near the Planck scale it begins carrying more weight than it can comfortably bear. A clock can help us again. Suppose you want to build faster and faster clocks. A pendulum clock is too slow for fine work. A quartz clock is much better. An atomic clock is better still, because atoms provide remarkably stable rhythms. Scientists can use transitions inside atoms as timekeepers, and those rhythms are so precise that they reveal effects from relativity in everyday height differences. Place one atomic clock slightly higher than another, and because gravity affects time, the two clocks will not tick at exactly the same rate. That is already a remarkable fact. But still, these clocks are unimaginably slow compared with a Planck scale clock. A Planck frequency clock would need to tick once every Planck time. But to produce or measure such a tick, the clock would require processes at an energy scale far beyond anything we can create. It would not be a simple technological challenge where we are waiting for better engineering. It would be a fundamental challenge because the energy required to make such a clock could collapse the usual distinction between a measuring device and a gravitational object. The clock might become so concentrated in energy that it could be hidden behind a tiny horizon, like a black hole. A clock that cannot communicate its ticks is not very useful as a clock, even if it is punctual in some unreachable sense. This brings us to one of the gentle paradoxes of ultimate measurement. To measure shorter times, we need higher frequencies. Higher frequencies imply higher energies. Higher energies, when concentrated too tightly, create stronger gravitational effects. Strong gravity changes time and can trap information. So the pursuit of the shortest possible time, or the highest possible frequency, may lead to a point where the measurement defeats itself. We try to make the tick sharper, but the tick becomes gravitationally hidden or conceptually unclear. We try to make the wave faster, but the wave becomes so energetic that space-time can no longer be treated as a simple background. This is not nature being mischievous, although it can feel that way. It is the result of combining the rules we already trust. Quantum theory links frequency with energy. Relativity links energy with gravity and space-time. Planck units emerge when these links are brought together. The surprise is not that the Planck frequency is large. The surprise is that largeness in frequency leads us back to smallness in time and length, and then into the gravitational structure of the universe. The fastest rhythm becomes a doorway into the deepest geometry. It is also worth noticing that Planck frequency is not the same kind of limit as the speed of light. The speed of light is a well-tested universal speed limit for signals and objects with mass in ordinary space-time. Planck frequency is more subtle. It is not usually presented as a proven rule saying no frequency above this can ever be written in any theoretical context. Instead, it marks the scale where a frequency above it would probably not have a clear meaning within our current framework. It is less like a road sign with a posted number, and more like the edge of a map where the paper fades into unfinished territory. This matters because physics has many different kinds of limits. Some are strict and experimentally confirmed in many settings. Some are practical, meaning we cannot reach them with current technology. Some are conceptual, meaning our existing ideas stop being reliable. Planck frequency belongs mostly to this last kind. It is a conceptual and theoretical boundary suggested by the constants of nature. It tells us that if we try to describe a rhythm faster than this, we're no longer safely using ordinary quantum theory or ordinary relativity. We're asking for quantum gravity, the missing theory that would describe the situation properly. The phrase highest frequency possible should therefore be heard with care. It does not mean that a scientist has watched every possible wave and found the final one. It means that, according to our best understanding, the Planck frequency is the highest frequency that can be associated with a meaningful Planck scale cycle before our familiar notions of time and space become unreliable. Beyond it, perhaps the correct theory would not speak in terms of frequency at all. Perhaps it would use information, relationships, networks, strings, loops, or something no one has named yet. The limit may not be a wall inside reality. It may be a wall inside our current language. Still, language is not useless. It can guide us. The idea of turning Planck time into Planck frequency teaches us that the tiniest possible interval and the fastest possible rhythm are inseparable. You cannot ask about one without meeting the other. Time and frequency are paired like the two sides of a breathing motion. One asks how long a cycle lasts, the other asks how many cycles fit into a larger interval. When the cycle length shrinks toward the Planck time, the frequency climbs toward the Planck frequency. That pairing lets us translate a question about the smallness of time into a question about the intensity of change. This translation is powerful because frequency appears all across physics. Atoms absorb and emit light at particular frequencies. Radio communication depends on controlled frequencies. Lasers rely on coherent light of very precise frequency. The cosmic microwave background, the ancient afterglow of the early universe, fills space with radiation whose frequency has been stretched by cosmic expansion. Gravitational waves, ripples in space-time itself, have frequencies that detectors on Earth can measure when black holes or neutron stars merge. Frequency is one of the great organizing ideas of modern science. It tells us how nature repeats, resonates, stores energy, and communicates. Planck frequency sits beyond all these familiar examples. It is not merely another entry on the spectrum waiting above gamma rays like the next shelf in a cupboard. The electromagnetic spectrum can be described across a vast range, but as we push toward the Planck frequency, the usual separation between quantum fields and gravity becomes questionable. A photon with such an extreme frequency would carry such extreme energy that it could not be treated as an ordinary particle of light passing through a passive spacetime. It would be in the territory where the photon's energy might strongly affect the geometry around it. So the spectrum itself may not extend upward forever in the simple way a chart suggests. Charts are useful, but they can trick us. A chart can draw a line continuing to the right, and our eyes assume the world continues in the same way. Frequencies rise, wavelengths shrink, energies increase. The pattern seems simple, but physical meaning may not survive unlimited extension. A map of Earth can continue northward only until the pole, and after that the word north changes its meaning. In a similar way, asking for frequencies beyond the Planck scale may be like asking to continue a direction after the coordinate system has reached its limit. The question may need a new language rather than a larger number. There is a calm humility in this. The universe has allowed us to understand an extraordinary amount. We can describe the behavior of light from distant galaxies. We can predict how atoms emit spectral lines. We can build clocks so precise that gravity's effect on time becomes visible across small height differences. We can measure gravitational waves from events that happened before human civilization existed. Yet the Planck frequency reminds us that there are still places where our understanding becomes provisional. Not because science has failed, but because science is honest enough to mark the border between what has been tested and what is still being sought. One might wonder whether Planck frequency has any direct role in nature. Did the early universe contain processes at or near this scale? Do black holes involve something like it near their deeper structure? Could quantum gravity leave faint traces in lower energy physics, like a distant echo of that unreachable rhythm? These are serious questions, though answers remain uncertain. The earliest moments of the universe may have involved Planck scale conditions, but we cannot simply observe those moments directly. Black holes may force quantum gravity to reveal itself, but their horizons also hide much from outside observers. Some theories suggest possible indirect signatures, but none has yet given us a complete and confirmed picture. Planck frequency remains less a measured tone than a theoretical horizon. That horizon is useful because it tells us where not to be careless. If someone says a wave can simply have any frequency at all, forever upward, Planck frequency asks whether that statement still makes physical sense. If someone says time can be divided endlessly into meaningful instants, Planck time asks whether measurement can actually support that idea. If someone imagines a perfect clock capable of resolving every possible change, Planck frequency asks what energy that clock would require and what gravity would do in response. In each case, the Planck scale does not merely provide an answer, it changes the question. This change of question is one of the most beautiful habits of physics, though we are keeping the beauty practical rather than decorative. A child asks why things fall, and the answer becomes gravity. A scientist asks what gravity is, and the answer becomes curved spacetime. Another scientist asks what spacetime does at quantum scales, and the answer is not yet known. Each answer deepens the next question. Planck frequency belongs to that chain. It begins as the fastest possible tick and becomes an inquiry into whether ticking itself is fundamental. There is no need to imagine this as frightening. It is not a violent edge waiting somewhere in space. It is a scale of description. Your room remains quiet. Your clock remains useful. Your breathing remains slow. Ordinary frequencies continue doing their ordinary work. The hum of electricity, the warmth of infrared light, the colours reaching your eyes, the silent radio signals passing through walls, all of these belong to realms where physics is confident and practical. The Planck frequency sits far beyond them, not interfering with daily life, but anchoring a deep question beneath it. In a way, every ordinary frequency is a softened cousin of the same idea. A rocking chair repeats slowly. A heartbeat repeats with living regularity. A musical note repeats fast enough to become pitch. Light repeats faster still and becomes colour. Atomic transitions repeat with such reliability that they define timekeeping. At each level, frequency lets nature be counted. Planck frequency asks what happens when counting reaches its ultimate theoretical speed. Is there still a process to count? Is there still a background of time in which counting occurs? Is there still a meaningful difference between one tick and the next? These questions are not decorative. They are exactly the kind of questions that appear when known physics approaches its edge. Turning time upside down, then, is not a mathematical trick we need to write on a board. It is a change in perspective. Planck time looks downward toward the smallest interval we can meaningfully discuss. Planck frequency looks upward toward the fastest rate of change that interval implies. One emphasizes brevity, the other emphasizes intensity. Together, they form a pair of signposts at the boundary where quantum mechanics, relativity, and gravity meet. They do not tell us the full story of what lies beyond, but they tell us that beyond this region our old habits must be revised. As the idea settles, the highest frequency possible becomes less like a final musical note and more like a warning that our familiar sheet music may no longer apply. A frequency needs time. A wave needs space. A measurement needs an instrument that does not destroy the meaning of what it measures. Near the Planck scale, all of these requirements begin to blur. The rhythm is so fast that it points beyond ordinary rhythm. The tick is so short that it points beyond ordinary ticking. And the energy is so concentrated that gravity, which usually waits patiently on cosmic scales, steps forward and changes the rules of the conversation. This is where the next part of the journey naturally leads. If Planck frequency marks the fastest meaningful rhythm suggested by our known constants, we have to ask why nature might prevent anything faster from making sense. The answer will not be a simple refusal written into the universe like a notice on a locked door. It will come from the way shorter times demand higher energies, how higher energies affect space-time, and how measurement itself becomes tangled with the thing being measured. The fastest tick is not just fast, it is heavy with consequence. The fastest tick is not just fast, it is heavy with consequence. To see why the universe may not allow a faster rhythm, we have to stay with that idea for a while, because it is the point where speed stops being a simple matter of quicker motion and becomes a matter of physical meaning. In ordinary life, a faster rhythm usually just means something is repeating more often. A hummingbird beats its wings faster than a swan. A violin string vibrates faster than a double bass string. A computer processor switches states faster than a person can blink. Nothing about this seems mysterious at first. If one thing can repeat quickly, why not imagine something repeating more quickly still? Why not continue forever, upward through faster and faster cycles, until the mind runs out of patience before nature runs out of possibility? That is exactly where physics begins to object, not loudly, but firmly. It is not enough for the mind to imagine a faster rhythm. The rhythm has to be carried by something physical. It has to be represented by a wave, a field, a particle, a clock, a signal, or some process that can actually exist within the rules of the universe. A rhythm is not just a number floating in emptiness. It belongs to a change, and change requires a world in which states can differ from one another. It requires time enough for a before and after. It requires space enough for variation. It requires energy enough to make the process real. And once energy enters the story, gravity quietly enters with it. At low and familiar frequencies, this connection is easy to miss. The beat of music carries energy, but not enough to bend space-time in any dramatic way. A radio signal carries energy, but its gravity is so tiny that for all practical purposes it can be ignored. Visible light carries more energy per packet than radio waves, but a lamp on a desk does not become a gravitational hazard. Even energetic radiation from cosmic sources can often be described without treating its own gravity as the main event. Most of the time, frequency can climb a long way before gravity seems to care. The universe gives us an enormous playground in which waves, vibrations, oscillations, and signals can behave as though space-time is a smooth stage beneath them. But the playground is not infinite. As frequency rises, the energy associated with each tiny wave packet rises too. That energy may begin spread out, harmless, part of a field moving through space. But if we insist on pushing the frequency toward the Planck scale, we're no longer talking about ordinary waves with ordinary consequences. We're talking about a rhythm so fast that the energy required to define it may be packed into a region of space so small that gravity can no longer be treated as a faint background effect. It becomes central. The wave no longer simply travels through space-time. It starts to challenge the stability of the space-time that gives the wave its meaning. This is one of the key reasons the universe may not allow a faster rhythm. A faster rhythm needs a shorter interval. A shorter interval needs a more energetic process if it is to be measured or physically realized. A more energetic process, squeezed into a smaller region, has stronger gravitational effects. Eventually, the attempt to sharpen the rhythm produces conditions where the energy may be hidden behind a gravitational boundary. In simple language, push too much energy into too small a space, and the system begins to resemble a black hole. It is not that nature posts a warning sign saying no faster rhythms beyond this point. It is more that the act of trying to make such a rhythm changes the game so completely that the old question no longer works. A black hole is often imagined as a cosmic monster, a collapsed star swallowing gas, dust, and unfortunate fictional astronauts. That picture is dramatic, but the deeper idea is more general. A black hole forms when energy or mass is concentrated tightly enough that a boundary appears from which light cannot escape. The details can be enormously complex, but the important part here is simple. Gravity can become so strong that it prevents information from leaving a region in the ordinary way. If a clock or wave were pushed to such extreme concentration that it created a tiny black hole, then its ticks or cycles could no longer be used by the outside world as a normal physical rhythm. A hidden tick is not a useful tick. A frequency sealed behind a horizon is not a frequency that can function like the waves and clocks we normally describe. This creates a kind of natural censorship against unlimited sharpness. To measure shorter and shorter times, we try to use higher and higher energies. But those energies, if concentrated enough, curve space-time more and more strongly. At the Planck scale, the measuring tool threatens to become part of the gravitational disturbance. The ruler bends, the clock warps, the signal traps itself. The more precisely we try to define a moment, the more the universe reminds us that measurement is not free. It has a cost, and at the deepest scale, that cost may be paid in the structure of space-time itself. There is a gentle, everyday comparison that helps, though like all comparisons, it must not be pushed too far. Imagine trying to see something very small in a dark room. You bring a lamp closer. The object becomes clearer. You bring a brighter lamp, better still. But now imagine that each increase in brightness also heats the object, shakes it, melts it, and eventually burns down the room. At some point, more light no longer means better seeing. The act of illumination destroys the condition needed for observation. At the Planck scale, measurement may face a similar problem. To see finer time, we need a more intense probe. But the probe may become so intense that it changes the time and space we meant to inspect. This is not just a limitation of human technology. It is not like saying our microscopes are not good enough yet, but future scientists with sleeker laboratories and better funding will simply solve it. Of course, future technology may reveal extraordinary things, and it would be foolish to underestimate clever people with patience and access to very cold equipment. But the Planck scale appears to involve a more fundamental difficulty. It arises from the rules themselves. Quantum theory tells us that probing smaller scales requires higher energies. Relativity tells us that energy affects gravity. General relativity tells us that gravity is the shape of spacetime. Put those ideas together, and the attempt to exceed the Planck frequency begins to look less like an engineering challenge and more like a conceptual boundary. The word boundary is important. It does not necessarily mean a hard wall made of tiny bricks at the bottom of time. It does not prove that the universe updates in discrete frames. It does not prove that every possible process must stop exactly at Planck frequency in the simple way a car stops at a gate. The honest statement is subtler. Planck frequency marks the scale where our ordinary ideas of frequency, time, energy, and space-time can no longer be trusted without a theory of quantum gravity. Beyond it, the familiar concept of a faster rhythm may not apply. Nature may not allow it because the conditions needed to define it dissolve the very framework in which frequency is measured. Frequency needs time as a background. It assumes that one cycle can be distinguished from another, that a process can repeat, that there is a meaningful interval between repetitions. But what if time itself is not smooth at the deeper scale? What if time is emergent, arising from something more basic? What if the geometry of space-time fluctuates so strongly near the Planck scale that the idea of a clean interval becomes blurred? Then asking for a rhythm faster than Planck frequency may be like asking for waves on a surface that has not yet become water. The words are familiar, but the situation does not support them. This is where the universe may be more subtle than any simple prohibition. It may not forbid faster rhythms in the sense of a rule imposed from outside. Rather, it may make the phrase faster rhythm physically empty beyond a certain point. A rhythm must have cycles. A cycle must have duration. Duration must be meaningful. If duration below the Planck time is not physically meaningful in our current description, then a frequency above the Planck frequency is not simply hard to produce, it may be hard to define. Physics is full of moments like this, where the limits of language and the limits of nature become tangled together. Consider temperature for a moment. Temperature is real. You can feel warmth and cold. You can measure temperature with instruments. It shapes weather, chemistry, biology, and the comfort of soup. But if you ask for the temperature of one isolated particle in the same way you ask for the temperature of a cup of tea, the question becomes awkward. Temperature is a property of many particles, a statistical idea that emerges from collective behavior. One particle has motion and energy, but temperature in the ordinary sense belongs to a group. The concept has a domain where it works, and a domain where it begins to lose meaning. Planck frequency may teach a similar lesson about time and rhythm. The idea of frequency works beautifully across many scales, but perhaps not beyond the scale where space-time itself loses ordinary smoothness. This possibility does not make the known universe less real. It makes it more layered. At our scale, time is smooth enough for clocks, memory, music, sleep, and the slow cooling of tea. At atomic scales, time is reliable enough for quantum transitions and precision measurement. At cosmic scales, time is woven with space and affected by gravity. At the Planck scale, time may become something we do not yet have the right picture for. Each scale has its own language. Problems arise only when we force one language to rule them all. The highest possible frequency also connects to the idea that there may be a shortest meaningful wavelength. A wave with a higher frequency often has a shorter wavelength, and at ordinary scales this relationship is harmless. Radio waves can be long, visible light is much shorter, gamma radiation is shorter still. Keep shrinking the wavelength in thought, and eventually it approaches the Planck length. A wave shorter than that may not be describable as an ordinary wave in space-time. If the wave is so compressed that it probes distances where space-time itself is expected to become quantum and uncertain, then the idea of a well-defined crest and trough may not survive. It is not that the wave is too tiny for our eyes. It may be too tiny for the old concept of distance. This matters because waves are not decorations on reality. They are one of the main ways physics describes reality. Quantum fields have wave-like behavior. Light is described through fields and quanta. Particles themselves are associated with wavelengths in quantum mechanics. When we say a wavelength becomes extremely small, we're also saying the associated energy becomes extremely high. That high energy, if localized, brings gravity into focus. The Planck scale is where this entire web tightens. Wave, particle, energy, gravity, space, and time become parts of one knot. A faster rhythm may therefore be blocked from several directions at once. From the time side, it would require intervals smaller than the Planck time, where ordinary duration may not be meaningful. From the energy side, it would require energies so extreme that gravitational effects cannot be ignored. From the space side, it would be associated with wavelengths near or below the Planck length, where the smooth geometry of space may not apply. From the measurement side, any attempt to observe it may create a disturbance large enough to hide or alter the thing being measured. These are not separate walls, but different faces of the same deep problem. There is also the issue of information. A rhythm can carry information only if its states can be distinguished. A signal must be able to leave traces, to be detected, to interact in a way that preserves some difference between one state and another. If a supposed rhythm is so fast that no physical system can distinguish its cycles without collapsing the description into quantum gravitational uncertainty, then it cannot function as information in the usual sense. The universe may not allow a faster rhythm because a faster rhythm could not be used to mark, transmit, or store anything in a physically meaningful way. A tick that cannot be distinguished from the conditions that blur ticking is not a tick in the ordinary sense. This is why Planck frequency is not merely about speed, but about distinguishability. To say that something repeats faster, we must be able to tell where one repetition ends and another begins. At the Planck scale, the distinction may be lost, not because our attention wanders, as it does during a long meeting, but because nature may not provide a stable background on which such distinctions can be drawn. The faster rhythm would be like trying to draw thinner and thinner lines on a surface that begins to shake, fold, and dissolve beneath the pen. Some theories of quantum gravity suggest that space and time have discrete structures at the smallest scales. In those pictures, a faster than Planck rhythm might be impossible in a fairly direct way, because there would be no smaller time steps for it to occupy. Other theories do not treat time as made of literal pieces, but still suggest that the Planck scale marks the breakdown of classical spacetime. In those pictures, faster rhythms might not be forbidden as steps beyond a smallest tick, but the concept of frequency would have to be replaced by something deeper. Either way, the conclusion is similar enough for our purpose. Planck frequency points toward a threshold where ordinary rhythm cannot simply be extended without change. The early universe may have come close to this threshold. If we trace cosmic history backward, the universe becomes denser and hotter, and the energy of its contents rises. There is a point beyond which our current theories cannot confidently describe what happened. This does not mean the universe was unknowable. It means the physics required is incomplete. Near the earliest moments, Planck scale processes may have mattered, and the familiar separation between particles moving through space-time and space-time itself may not have existed in the form we know. Asking about rhythms faster than the Planck frequency in that setting may be like asking what the weather was before the atmosphere had the properties that make weather possible. Black holes may also bring us close to the same frontier. Around a black hole, gravity strongly affects time. Near the horizon, clocks appear to behave strangely from the perspective of distant observers. Deep questions about black hole entropy, information, and evaporation suggest that gravity, quantum theory, and thermodynamics are connected in ways not yet fully understood. The Planck scale appears again and again in these discussions, not as a decorative number, but as a sign that the ordinary tools are nearing their limits. If the universe refuses a faster rhythm, black holes may be one of the places where that refusal becomes physically meaningful, because they show how energy, information, and space-time boundaries are tied together. It is worth keeping the tone calm here, because phrases like highest possible and ultimate limit can sound dramatic enough to wake the cat. The Planck frequency is not a cosmic emergency. It is not a vibrating wall at the edge of existence. It is a theoretical scale. It tells us that beyond a certain point, frequency cannot be understood without quantum gravity. It may be the highest meaningful frequency in nature, but the word meaningful is carrying much of the weight. We're not just ranking rhythms. We're asking what kinds of rhythm can belong to a universe with quantum fields and dynamical space-time. In ordinary terms, the universe may not allow a faster rhythm because faster is not free. Faster demands shorter. Shorter demands sharper. Sharper demands more energy. More energy curves space-time. Curved space-time changes time itself. At the extreme, the attempt to make the rhythm faster removes the stable stage needed for rhythm. That chain of reasoning is simple in outline but profound in consequence. It suggests that nature protects itself from infinite subdivision, not by hiding the next smaller piece, but by making the very act of seeking it transform the question. This is one of the reasons the Planck scale feels so different from other scientific frontiers. The deep ocean is hard to explore, but it is still there in a familiar sense, with water, pressure, darkness, and creatures. Distant galaxies are hard to reach, but telescopes can gather their light. The centre of Earth is inaccessible, but seismic waves give clues. The Planck scale is difficult in a more radical way. It is not just far away or well hidden. It is where the meanings of distance, time, and measurement themselves may need revision. We cannot simply travel there with a better engine, or look there with a stronger lens. A stronger lens, in this case, may create the very gravitational problem that prevents the looking. There is a humble lesson in that, and it is not only for physicists. We often assume that more intensity gives more clarity, more speed, more power, more precision, more control. But at the deepest scale, nature may say that clarity cannot be forced indefinitely. There are questions that change when pressed too hard. The Planck frequency is a scientific version of that lesson. A faster rhythm is not always a better rhythm. Beyond a certain point, it may stop being a rhythm at all. Yet this does not make the Planck frequency a dead end. It makes it a clue. Every time physics finds a limit, it finds a new structure. The speed of light led to space-time. Quantum uncertainty led to the strange architecture of the microscopic world. The link between entropy and black holes led to deep ideas about information and gravity. The possible limit represented by Planck frequency may point toward the theory that unifies quantum mechanics and general relativity. It may tell us whether time is fundamental, whether space is granular, whether information is the root of geometry, or whether reality is built from principles we have not yet learned how to phrase. So the universe may not allow a faster rhythm not because it lacks imagination, but because the ingredients needed for rhythm are themselves limited. Time may not be divisible without end in a physical sense. Energy cannot be concentrated without gravitational consequence. Space may not remain smooth below the Planck scale. Measurement may not be able to stand outside the thing it measures. All these facts lean toward the same quiet conclusion. There may be a deepest tempo beyond which the word tempo no longer applies. And as we move onward, this prepares us for a more delicate question. If a faster rhythm may not be allowed because waves become too energetic, too compressed, or too disruptive to space-time, then what happens to the idea of waves themselves at these extremes? A wave is such a familiar tool in physics that we sometimes forget it has assumptions built into it. It needs a background, it needs a scale, it needs a way to vary. At the edge of the Planck domain, even that simple picture begins to strain, and the next step is to ask when a wave becomes too small to make sense. At the edge of the Planck domain, even the simple picture of a wave begins to strain. That may sound surprising because waves are among the most familiar ideas in all of physics. They are everywhere. Water rises and falls against a shore. Sound moves through air as pressure changes. Light travels across space with electric and magnetic fields changing together. Even matter, at the quantum level, has wave-like behavior. A wave is one of the most useful ways the universe allows us to describe change, motion, energy, and communication. It is so useful that we can forget it is still a model, and like every model, it has conditions under which it works. A wave needs room to be a wave. It needs some way to vary from place to place and from moment to moment. A wave on water needs the surface of the water. A sound wave needs a medium such as air, water, or solid material. Light does not need air, but it still needs space-time as the stage on which its fields can change. A quantum wave is more subtle, because it is not always a physical ripple in the everyday sense. It can describe probabilities, possibilities, and the behavior of fields. Still, even there, we use ideas of distance, duration, frequency, and wavelength. We ask how spread out it is. We ask how quickly it changes. We ask what energy it carries. These questions work beautifully across an enormous range of nature. But when waves are pushed to extremely short scales, the usual picture becomes less comfortable. Imagine a long ocean swell rolling calmly toward a beach. It has a clear shape. You can see one crest, then another after that. Now imagine smaller ripples on a pond. They are still waves. Then imagine vibrations in a string, sound waves in air, light waves far beyond what your eyes can follow, and radiation with wavelengths far shorter than visible light. In each case, we can still speak of crests and cycles in some useful way, even if the details become more mathematical and less visual. The wave may not be something your senses can picture directly, but the concept still behaves. As the wavelength becomes shorter, however, the energy associated with the wave becomes larger. This has been one of the central lessons of quantum physics. Light of higher frequency carries more energy in each packet. That is why different kinds of radiation behave so differently. Radio waves can pass around buildings and carry music, voices, navigation signals, and the soft background chatter of modern life. Visible light lets us see the room around us. Ultraviolet light can affect chemical bonds and damage skin. X-rays can pass through soft tissue and reveal bones. Gamma rays can come from nuclear processes and violent cosmic events. The climb upward in frequency is also a climb upward in energy, and energy is never just a harmless label. For a long time, even very high energy waves can still be treated using known physics. We can study them. We can detect them. We can build instruments that respond to them. Particle accelerators can create energetic collisions. Telescopes can observe radiation from distant and extreme events. The universe itself provides laboratories far beyond anything humans could build on Earth, with black holes, neutron stars, supernovae, and jets from active galaxies. In all these cases, waves and particles can be described with impressive success. The mathematics may be difficult, but the basic language still holds. Near the Planck scale, the situation changes because the wavelength becomes so short that it approaches the scale at which space-time itself may no longer be smooth. A wave shorter than the Planck length is not simply a very tiny wave, like a miniature ripple waiting to be magnified. It is a wave whose meaning depends on a background of space and time that our current theories can no longer describe with confidence. To say that a wave has a wavelength, we need a meaningful idea of distance. To say it has a frequency, we need a meaningful idea of time. To say it carries energy, we need a way to describe how that energy affects the rest of the universe. At the Planck scale, all three ideas become tangled. This is the point where the phrase too small to make sense becomes important. It does not necessarily mean nature forbids every possible deeper structure. It does not mean there is nothing below the Planck length in any absolute sense. It means that the ordinary wave picture may stop being the right tool. A wave may become too small for the assumptions behind the word wave. The concept may be like a ruler trying to measure a distance after the surface it rests on has begun to fluctuate. The ruler is not useless in general. It is useless for that particular situation. In everyday physics, space-time is usually treated as smooth. Even in general relativity, where space-time can bend and curve under the influence of mass and energy, it is still described as a continuous fabric. A planet curves space-time gently around itself. A star curves it more strongly. a black hole curves it so strongly that an event horizon forms. But the geometry itself is still usually imagined as smooth, like a flexible sheet rather than a pile of grains. Quantum mechanics, on the other hand, tells us that the microscopic world does not behave in a completely smooth and definite way. Fields fluctuate. Measurements have limits. Particles show wave-like and particle-like properties depending on how they are observed. When these two ideas meet at the Planck scale, the smooth sheet may no longer be smooth. Some physicists use the term quantum foam to describe what spacetime might be like at these tiny scales. It is a vivid phrase, but it should not be taken too literally. No one is saying that if you could shrink yourself small enough, you would see soap bubbles floating under reality. The phrase is a way of suggesting that spacetime might be restless, fluctuating and uncertain at the smallest scales, rather than calm and continuous. If that is true, then a wave with a wavelength at or below that scale would not be moving through a smooth ocean. It would be trying to ripple through something whose very geometry is uncertain. The ocean comparison helps for a moment. A wave on the sea makes sense because the sea surface is much larger and smoother than the wave's small details. If the water surface were broken into violently shifting fragments smaller than the wave itself, the wave would lose its clean identity. It would no longer be obvious where one crest begins or where the next ends. The disturbance would still exist in some form, but the ordinary description would fail. At the Planck scale, spacetime might present a similar problem. A wave smaller than the scale at which spacetime remains smooth may not be a wave in the usual sense. It may require a deeper description, one in which space, time, and energy are not separate ingredients. There is another route to the same difficulty. To make a wave with a very short wavelength, we need very high energy. At first, this energy simply makes the wave more penetrating, more powerful, or more capable of interacting with matter. But if the wavelength becomes extremely short, the energy becomes concentrated into an extremely small region. Gravity responds to energy. It does not care whether that energy comes in the form of matter, radiation, motion, pressure, or fields. Energy gravitates. At the Planck scale, the energy associated with such a tiny wavelength would curve spacetime strongly. The wave would not merely reveal geometry, it would help create or distort it. This is where the simple idea of looking closer breaks down. In ordinary life, if you want to see smaller details, you use shorter wavelength light. A magnifying glass improves vision. A microscope uses light to reveal cells. An electron microscope uses the wave-like behavior of electrons to reveal smaller structures. The rule seems clear. Shorter wavelength gives finer detail. But keep pushing that rule and it leads into trouble. At some point, the probe you use to see smaller things carries so much energy that it changes the thing you are trying to see. Near the Planck scale, it may change the geometry of spacetime itself. The wave you hoped would be a delicate measuring tool becomes a gravitational event. This is not just a technical inconvenience, it is a sign that measurement has reached a conceptual limit. If a wave becomes energetic enough to form a tiny black hole, then the information you wanted may be hidden behind a horizon. A black hole is not merely a place where gravity is strong, it is a boundary problem for information and observation. From outside, certain details cannot escape in the ordinary way, so if trying to create a wave small enough to probe below the Planck scale produces a horizon, then the attempt to look closer has made the view worse, not better. The instrument closes the curtain. This may sound like nature is teasing us, but it is more accurate to say that the rules are consistent in a way that surprises us. Quantum physics says shorter wavelengths correspond to higher energies. General relativity says energy affects spacetime. When both statements are taken seriously at once, the idea of arbitrarily short waves becomes suspect. The wave is no longer a harmless line drawn on a stable background. It is an energetic object in a universe where energy shapes the background itself. The picture folds back on itself. That folding is one reason the Planck scale is so central to quantum gravity. In most physics, we can choose which theory matters most. If we are describing a falling stone, ordinary gravity is enough. If we are describing an electron in an atom, quantum mechanics is enough. If we are describing light bending around the sun, general relativity is enough. But if we are describing a wave with a Planck scale wavelength, we cannot choose so easily. The wave is quantum because it is small. It is gravitational because it is energetic. It is relativistic because space and time cannot be separated from the description. Every major idea arrives at once and none can be ignored. This is why a wave can become too small to make sense within our current theories. It is not that waves are wrong. Waves remain one of the great successes of physics. They describe sound, light, matter, fields, and gravitational ripples across space. But at the Planck scale, the background assumptions behind wave descriptions may fail. We may need a theory where the word wave is replaced by something deeper, or where waves emerge only when many smaller ingredients behave collectively. Just as temperature emerges from the motion of many particles, perhaps space-time and its waves emerge from a deeper structure that does not itself look like space, time, or waves. Different approaches to quantum gravity offer different possibilities. Some suggest that the smallest structure of space might be described by networks, loops, or discrete relationships. Others suggest that particles are not point-like objects but extended structures, and that this extension prevents the infinities that appear when we try to force physics into arbitrarily small points. Other ideas treat space-time as something built from information, entanglement, or causal order. These approaches differ, and none has yet become the confirmed final theory. But they share a suspicion that the familiar smooth stage of space and time is not the whole story. If that suspicion is right, then waves at the Planck scale are not simply tiny waves. They are clues that the stage itself has deeper construction. A helpful comparison comes from sound. Sound is a wave in matter. In air, it is a pattern of pressure changes moving through molecules. At ordinary scales, we do not need to track each molecule. We can speak of smooth pressure waves, and the description works. But if we tried to make a sound wave with a wavelength smaller than the spacing between molecules, the ordinary idea of sound would break down. Sound depends on the collective behavior of many molecules. Below that scale, you are no longer describing a smooth pressure wave. You're dealing with individual molecular motion. The word sound has left its proper domain. This comparison is not perfect, because space-time is not air, and Planck scale physics is far more mysterious than ordinary molecules, but it gives the right kind of lesson. A concept can be real and useful without applying at every possible scale. Sound is real. It wakes people, soothes people, carries music, and occasionally reminds us that the refrigerator is making a noise it did not make yesterday. But sound is not meaningful below the scale where the medium can support it. In a similar way, waves in space-time or fields may be real and useful across enormous ranges, yet not meaningful below the scale where space-time and fields have their usual form. This way of thinking avoids unnecessary drama. The Planck scale does not make waves disappear from the universe. It simply warns us not to stretch the wave picture beyond its domain. Physics is full of domain boundaries. Classical mechanics works beautifully for slow objects much larger than atoms. It fails for extremely fast objects or very small ones. Newtonian gravity works well for many practical problems. It fails near black holes, or when extreme precision is needed. Thermodynamics works for large collections of particles. It is not the right language for one isolated molecule. A theory does not have to apply everywhere to be powerful. It has to tell us where it applies and where a deeper theory is needed. The wave picture has been so successful that its boundary is especially interesting. Light as a wave helped explain interference, diffraction, and colour. Light as particles helped explain the photoelectric effect and quantum energy exchange. Matter waves helped explain atoms, chemistry, and the strange stability of the microscopic world. Quantum fields extended the idea further, making particles appear as excitations of underlying fields. Even gravity in weak disturbances can travel as waves through spacetime, as gravitational wave detectors have now confirmed. Waves are not a small part of physics. They are one of its main languages. When that language begins to fail, it is a serious event. It suggests that the deepest reality may not be simply made of smaller and smaller waves. Or if waves remain, they may not be waves in space and time, but waves of something more fundamental. This is difficult to picture because our minds are trained by daily experience. We imagine things located somewhere. We imagine events happening at some time. We imagine changes spreading through space. A deeper theory may not begin with those assumptions. It may produce them as large-scale results. The way smooth water appears from countless molecules that do not themselves behave like a smooth surface. This is where the story connects back to Planck frequency. A frequency above the Planck frequency would imply a wavelength below the Planck length and a cycle shorter than the Planck time, at least in the ordinary way of thinking. But if wavelengths below the Planck length do not have the usual meaning, then higher frequency does not simply mean a more extreme version of the same kind of wave. It may be like trying to speak of a sound higher than what the medium can support, or a ripple smaller than the surface can define. Nature may not reject the request with a dramatic thunderclap. It may simply leave the terms of the request undefined. There is also a link to the way infinities appear in physics. Many theories, when pushed too far, produce infinite quantities, infinite energy, infinite density, infinite curvature. Infinities are often signs that a theory is being used outside its proper range. They are not always proof that nature contains an actual infinity. Sometimes they are warnings that the model has reached its breaking point. The Planck scale may be where the infinities of points like thinking and unlimited division are softened or replaced by a deeper structure. If waves cannot become arbitrarily small, some of these extreme infinities may be avoided in the final theory. This is one reason physicists are interested in whether the Planck length acts like a minimum length. If there is a minimum meaningful length, then no wave could have a physically meaningful wavelength shorter than that. This would naturally limit frequency and energy in certain ways. But again, the honest view is careful. We do not yet know whether there is a literal minimum length. Some theories suggest it. Others suggest a more subtle limitation, where length can remain mathematically continuous, but measurement below the Planck scale becomes impossible or meaningless. Either way, the Planck scale still plays the role of a threshold. A small wave can also challenge causality, the ordering of cause and effect. In ordinary space-time, causes and effects are arranged according to light cones, which tell us what can influence what. This structure depends on space-time geometry. If that geometry fluctuates at the Planck scale, then the simple ordering of events may become less definite. A wave cycle that is shorter than the scale on which time has a stable order may not represent a clean sequence. It becomes difficult to say what one cycle means when before and after are themselves subject to quantum uncertainty. This is another reason faster and smaller rhythms may not survive unchanged. The more we look at it, the more the phrase "too small to make sense" reveals itself as a serious scientific caution. It is not an excuse to stop thinking. It is an invitation to think more precisely. What do we mean by a wave? What background does it require? What makes a wavelength measurable? What makes a frequency distinguishable? What happens when the energy of measurement changes the geometry of the measured region? What happens when space-time itself is no longer smooth? These questions are not signs of failure. They are the road toward a deeper theory. There is a quiet parallel with the history of atoms. Before atoms were understood, matter seemed continuous. You could cut a piece of chalk in half, then half again in thought, and imagine continuing forever. But chemistry and physics revealed that matter has structure at small scales. The continuous appearance of matter is an emergent convenience. It works for hands, tables, and chalkboards, but not for everything. Space and time may have a similar surprise waiting at the Planck scale. They may look continuous to us because we live far above the scale where their deeper structure matters. If so, waves are like patterns on the surface of a deeper sea. At large scales, they are clean, measurable, and meaningful. At extremely small scales, the surface may not be a surface anymore in the ordinary sense. The waves may dissolve into the underlying structure from which space, time, and fields arise. We do not yet know how to describe that structure fully, but Planck's scale reasoning tells us that it is there, or at least that something must replace our current picture there. For now, the safest and most useful conclusion is this. Waves become too small to make sense when their wavelength is pushed toward the scale where space-time itself can no longer be assumed smooth, and when the energy required to define them becomes strong enough for gravity to reshape the situation. At that point, a wave is not simply a smaller version of a familiar ripple. It is a question aimed at the foundation of reality. Our current physics can guide us to the threshold, but it cannot yet carry us across with certainty. The strange thing is that this limit is not only about smallness, it is about the meeting of opposites. The smallest wavelength implies the highest energy. The tiniest interval implies the fastest frequency. The most microscopic scale summons gravity, the force we usually associate with planets and stars. The search for the smallest wave leads not away from black holes and cosmology, but toward them. That is why the next step in the story belongs naturally to black holes, quantum foam, and the edge of physics, where the universe shows us that the very small and the very massive are not as separate as they first appear. The search for the smallest wave leads into places where the very small and the very massive are no longer separate subjects. That may feel backwards at first. We usually imagine black holes as enormous, heavy, distant things, born from the collapse of stars and surrounded by the dramatic language of astronomy. We imagine the Planck scale as the opposite, a realm so tiny that ordinary matter seems huge beside it. One belongs to the night sky, the other belongs to the hidden floor of reality. Yet the deeper we follow the idea of the highest possible frequency, the more these two worlds begin to meet. The tiny and the immense turn out to be connected by gravity, energy, and the question of what space and time are made of. A black hole begins with a simple but severe idea. If enough mass or energy is packed into a small enough region, gravity becomes so strong that not even light can escape once it passes a certain boundary. This boundary is called the event horizon. It is not a solid surface like the skin of a planet. You could cross it without hitting a wall, at least if the black hole were large enough and the tidal forces were gentle at the crossing. But after crossing it, every possible future path points inward. Light cannot climb back out. Signals cannot return to distant observers. The event horizon is a boundary in causality, a border in what can influence what. This matters for Planck frequency because the attempt to create or describe an extremely tiny, extremely fast wave involves energy concentrated into a tiny scale. High frequency means high energy. Short wavelength means concentrated structure. Keep pushing the wavelength smaller and the frequency higher, and gravity can no longer be ignored. Eventually, the energy needed to define such a small wave may itself curve spacetime so strongly that a horizon forms. The thing you tried to use as a probe becomes hidden behind its own gravitational boundary. The wave you wanted to sharpen becomes less like a clean ripple and more like the seed of a black hole. This is one reason black holes are not merely cosmic curiosities in this story. They are nature's warning that energy and information cannot be squeezed without consequence. A black hole says that there is a limit to how much can be packed into a region before the geometry of space-time changes completely. The Planck scale says something similar in a smaller and more theoretical language. If you try to pack a wave, a clock or a measurement into an interval shorter than Planck time or a distance shorter than Planck length, the energy required may make the measurement collapse into the gravitational realm. The smallest clock and the darkest object in the universe are linked by this shared rule. Concentration matters. It is helpful to pause with the event horizon, because it is one of the cleanest places where time stops behaving in the ordinary way. Far from a black hole, a clock can tick normally, or at least normally enough for daily life. Near a black hole, the story changes. From the viewpoint of a distant observer, a clock falling toward the horizon appears to slow down. Its light becomes stretched, dimmed, and reddened. It seems to approach the horizon more and more slowly, never quite crossing in the distant observer's view. But for the falling clock itself, time continues locally. It crosses the horizon in a finite amount of its own time, unaware of any hard surface at that exact boundary. This difference is not a trick of bad observation, it is part of relativity. Time depends on location, motion, and gravity. The event horizon therefore teaches us that time is not a universal background. It is tied to space-time geometry. If gravity can change how clocks compare with one another, then the idea of the fastest possible clock cannot be separated from gravity. Near the Planck frequency, the clock is not just fast. It is energetic enough that it may create a gravitational environment around itself. The question becomes self-referential in a physical sense. A clock used to measure time may affect the time it measures. A wave used to probe space may bend the space it probes. At ordinary scales, this effect is tiny. At the Planck scale, it may be decisive. Black holes also connect with another deep idea, the idea that information and area are related. In everyday life, if you want to store more information, you usually imagine needing more volume. A library holds more books than a drawer. A hard drive with more memory holds more files. But black hole physics suggests something stranger. The amount of information associated with a black hole appears to be connected not to the volume inside it, but to the area of its horizon. This idea has led physicists to suspect that space-time, gravity, and information are related in ways far deeper than ordinary intuition suggests. It is as though the horizon of a black hole is not just a boundary of escape, but also a ledger of what the black hole can contain. This has a quiet connection to the Planck scale. The natural units used to describe black hole information involve Planck-sized areas. When physicists speak about the maximum amount of information that can be associated with a region, the Planck scale appears as the natural counting scale. This does not mean the horizon is literally covered in tiny tiles in a simple visual way, though some approaches to quantum gravity explore ideas that sound a little like that. It means that when gravity, quantum theory, and information come together, the Planck scale keeps returning. It appears as a sign that the smooth geometry of space-time may have a deeper informational structure. A black hole also has temperature. That statement sounds wrong the first time one hears it. A black hole is supposed to be black, a perfect absorber, a region from which nothing escapes. But quantum theory changes the picture. When quantum fields are considered near the event horizon, black holes are predicted to emit a faint thermal radiation. This radiation is known as Hawking radiation. For large black holes, it is incredibly weak, far colder than the cosmic background around them. But the principle matters enormously. It shows that black holes are not simply classical gravitational traps. They are thermodynamic objects. They have temperature, entropy, and a slow path toward evaporation. Now the story becomes even more tangled, in the best scientific sense. Black holes involve gravity. Hawking radiation involves quantum fields. Entropy involves information and thermodynamics. Time is affected by the curved geometry near the horizon. The Planck scale appears when we ask what happens near the final stages of evaporation, or near the deepest microscopic description of the horizon. A black hole is therefore one of the few natural arenas where the ingredients of quantum gravity are not optional. It forces them into the same room and politely closes the door. For a large black hole, the curvature at the horizon can be relatively gentle. A supermassive black hole can have an event horizon so vast that crossing it would not immediately feel dramatic, though the final destination would remain unfortunate for anything hoping to send postcards. But as black holes become smaller, their temperature rises and quantum effects become more important. A tiny black hole, if such an object could exist, would be hotter and more quantum in its behaviour. Near the Planck scale, the very concept of a small black hole becomes difficult to describe using known physics. We would need quantum gravity to say what truly happens. Does it evaporate completely? Does it leave a remnant? Does information escape in subtle correlations? Does the old idea of a singularity disappear? These questions sit near the edge of what physics can currently answer. The singularity is another word that must be treated carefully. In the classical theory of general relativity, the centre of a black hole can lead to a singularity, a place where density and curvature become infinite in the mathematics. But infinities in physics often signal that a theory has been pushed beyond its proper range. They are like a map tearing when stretched too far, not necessarily a faithful picture of nature. Most physicists suspect that a complete theory of quantum gravity would replace the classical singularity with something finite, though no final confirmed answer exists. The Planck scale is where that replacement should matter. It is where the smooth classical picture becomes unable to carry the full burden. This is where quantum foam enters the story. If we try to examine space-time at extremely tiny scales, some ideas suggest that it may not remain smooth and calm. Instead, it may fluctuate. Geometry itself may become uncertain. Tiny changes in curvature, topology, or causal structure might appear and vanish. The phrase quantum foam was introduced to capture this rough possibility, not as a precise photograph, but as an image of space-time becoming turbulent at the smallest scales. Like many images in physics, it is useful as a doorway and dangerous as a literal picture. We should not imagine ordinary foam made of bubbles, nor little holes fizzing under the floor of the world. We should imagine that the smooth stage of space-time may have quantum restlessness when viewed at scales near the Planck length and Planck time. If space-time is foamy in this sense, then Planck frequency becomes even harder to exceed in a meaningful way. A frequency requires a stable notion of time over which cycles can occur. A wavelength requires a stable notion of distance over which a pattern can extend. If distance and duration fluctuate at the scale of the pattern itself, then the wave cannot be described as a neat repeating structure. It is like trying to measure the width of a ripple on a pond while the pond surface is boiling, freezing, folding, and rearranging faster than the ripple can define itself. The problem is not merely that the ripple is small, it is that the background needed to call it a ripple is no longer well behaved. Quantum foam also suggests why empty space may not be truly empty. In quantum field theory, what we call the vacuum is not simple nothingness. It is the lowest energy state of fields, and it has fluctuations. Particles are not little pebbles placed inside emptiness. They are excitations of fields that fill space. Even the vacuum has structure. At ordinary scales, these fluctuations are usually subtle, though they can produce measurable effects. Near the Planck scale, if gravity itself must be quantum, then the vacuum structure of space-time may become far more complex than our ordinary idea of emptiness. Empty space may be less like a blank sheet and more like a calm-looking sea whose surface hides countless microscopic motions. This is not an invitation to imagine chaos without rules. Quantum fluctuations are not random magic. They're governed by mathematical structures, probabilities, symmetries, and constraints. The difficulty is that we do not yet have the final mathematical structure for quantum spacetime. We have powerful partial languages. We have quantum field theory on curved spacetime, which lets us study fields in a gravitational background. We have general relativity, which lets us study the geometry produced by mass and energy. We have candidate theories of quantum gravity that try to go deeper, but the complete experimentally confirmed description of space-time at the Planck scale remains unfinished. That unfinished state is what we mean by the edge of physics. It is not the edge of reality. Reality does not stop where our equations become difficult. It is the edge of our current understanding, the place where the tools we trust begin to disagree or lose clarity. The edge of physics is a fruitful place. It is where old concepts are tested most severely. It is where time, space, matter, energy, and information stop behaving like separate ideas, and become aspects of a single unsolved question. Black holes are especially valuable at this edge because they make the unsolved question visible in several ways at once. They bend time, they hide information behind horizons, they possess entropy and temperature, they may evaporate through quantum effects, they produce singularities in classical theory that almost certainly require quantum gravity. They connect the largest astronomical objects to Planck scale units. They are not just objects in space, they are laboratories for the deep structure of space and time, although not laboratories we can control with switches and notebooks. One of the most famous puzzles connected to black holes is the information problem. In quantum mechanics, information about a physical system is not supposed to be destroyed. It can become scrambled, hidden, or extraordinarily difficult to recover, but the evolution of the system preserves it in a deep sense. Black holes appear to challenge this idea. If matter falls into a black hole, and the black hole later evaporates as seemingly thermal radiation, what happens to the detailed information about what fell in? Is it lost? Is it encoded subtly in the radiation? Is it stored at the horizon? Is the classical picture of the black hole interior incomplete? Decades of work have sharpened this puzzle, and many physicists now suspect that information is preserved, but the exact mechanism remains deeply connected to quantum gravity. This matters for Planck frequency, because the same boundary of meaning appears. Information cannot be stored, transmitted, or resolved without physical degrees of freedom. If there is a maximum amount of information that can fit into a region before it becomes a black hole, then nature may impose limits on how finely reality can be divided into distinguishable states. Frequency is about distinguishing cycles in time. Wavelength is about distinguishing changes in space. Information is about distinguishable alternatives. At the Planck scale, these ideas begin to overlap. The highest frequency is not only about the fastest vibration, it is about the finest possible distinction the universe can support. The holographic principle grew from black hole thinking and suggests an even more surprising possibility. It proposes that the information contained in a region of space may be represented on its boundary, not throughout its volume in the way ordinary intuition expects. This does not mean the world is a simple hologram like a shiny sticker. It means that the deeper counting of information in a gravitational universe may be lower dimensional than it appears. The idea has become important in theoretical physics because it hints that space-time itself might emerge from more basic quantum information. If that is true, then quantum foam is not merely space-time bubbling at small scales. It may be a sign that space-time is not fundamental in the way we usually imagine. For a calm night of science, we do not need to solve the holographic principle, which is fortunate because many very awake people are still working on it. What matters here is the direction of the lesson. Black holes teach us that space-time, information, and quantum theory are intertwined. Planck scale thinking teaches us that the highest frequencies and smallest intervals cannot be understood without that intertwining. Quantum foam suggests that the smooth background of the universe may be an approximation, reliable at large scales, but incomplete at the smallest. Together, these ideas place Planck frequency at the boundary between known physics and whatever deeper structure remains to be discovered. There is a strange reversal in all of this. We began by asking about a rhythm so fast that it seems almost mechanical, like an ultimate clock. But the answer leads away from machines and into horizons, entropy, fluctuating geometry and information. A simple clock counts repeated changes. A Planck scale clock would force us to ask what change means when time itself may be quantum. A simple wave repeats across space. A Planck scale wave would force us to ask what space means when geometry may fluctuate. A simple measurement gives information. A Planck scale measurement would force us to ask how much information can be contained before gravity forms a boundary. The closer we get to the fastest rhythm, the less the universe resembles clockwork in the old sense. This does not make physics vague, it makes it demanding. The fact that we do not yet have a final theory does not mean anything goes. Quite the opposite. The Planck scale is constrained by what we already know. Any future theory must reproduce the successes of quantum mechanics. It was an accurate description at its scale, but it was not the deepest description. Spacetime may be similar. At our scale, it is smooth enough for planets, clocks, and light beams. At the Planck scale, the individual ingredients of geometry, whatever they are, may become important. Quantum foam is the rough name for the possibility that the smooth glow breaks into a deeper pattern. Black holes may be where the city lights become visible from both scales at once. A large black hole is a smooth object in general relativity, described by mass, spin, and charge. Yet its entropy suggests microscopic states. Its radiation suggests quantum behavior. Its horizon suggests information accounting. Its singularity suggests the breakdown of classical smoothness. It is both simple and profoundly complicated. That combination is why black holes are so beloved by theoretical physicists and so useful in this story. They take the farthest abstractions and give them a gravitational shape. There is also an emotional reason black holes fit a sleep science journey. They remind us that the universe is not required to be intuitive to be lawful. A black hole can be invisible in the ordinary sense, and yet reveal itself through the motion of stars, the glow of falling gas, gravitational waves from mergers, and the shadow cast against hot surrounding material. Quantum foam may be unobservable directly with current instruments, yet it may be hinted at by the need to reconcile theories. Planck frequency may never be heard or measured as a normal rhythm, yet it helps define the edge of meaningful description. Not everything real or useful must be directly graspable by the senses. Some things are known by the way they shape the rules around them. As we sit with this, the highest possible frequency begins to look less like a lonely number and more like a meeting place. On one side are waves, fields, and clocks. On another side are horizons, gravity, and the bending of time. On another are quantum fluctuations and the uncertain vacuum. On another are information, entropy, and the question of what the universe can store or reveal. Planck frequency stands where all these paths approach one another. It tells us that a faster rhythm may not be allowed because beyond this scale the separate roads merge into unknown terrain. The edge of physics is not silent exactly. It is full of hints. Black holes hint that information and geometry are related. Quantum theory hints that emptiness has structure. Relativity hints that time is part of a dynamic space-time, not a universal background. Thermodynamics hints that the flow of time and the spread of information are connected. Cosmology hints that the early universe passed through conditions where our current descriptions fail. The Planck scale gathers these hints into one region. It does not answer them, but it keeps them from drifting apart. And that is why this part of the journey matters before we move toward the great silence beyond measurement. Black holes show us that too much energy in too little space changes what can be known. Quantum foam suggests that too small a scale may change what space and time even are. The edge of physics reminds us that some limits are not merely technological. They are built into the relationship between measurement and reality. The fastest rhythm cannot be understood only by making clocks faster in imagination. It must be understood through the gravitational cost of asking time to reveal itself too finely. The fastest rhythm cannot be understood only by making clocks faster in imagination. It has to be understood through the gravitational cost of asking time to reveal itself too finely. That cost leads us into a strange quiet place. Not quiet because nothing is happening, but quiet because beyond a certain depth, the universe may no longer answer in the language our instruments know how to ask. Measurement is one of the great powers of science. It turns curiosity into numbers, guesses into tests, and vague wonder into something that can be checked by different people in different laboratories. Yet measurement is not magic. It is a physical act. It requires contact, energy, comparison, memory, and a signal that can travel from the thing being measured to the one doing the measuring. When we reach the Planck scale, all of that becomes uncertain. In everyday life, measurement feels simple because the world is generous with information. A ruler can measure a table without changing the table in any important way. A thermometer can measure the temperature of a room without making the room noticeably warmer or colder. A clock can measure the length of a conversation without altering the conversation, unless someone keeps looking at it, which is a different problem and more social than physical. Our tools are usually small disturbances compared with the things they measure. This is why common sense tells us that measurement is passive. We imagine the world already has its properties, sitting there patiently, and the instrument merely reads them out. Modern physics has taught us to be more careful. At small scales, measurement is not just looking, it is an interaction. To know where something is, you must in some way let it affect your detector, or let your detector affect it. To know how it changes, you must compare it with a physical process that changes too. To know the time of an event, a clock must be part of the event's description. None of this is optional. Information does not arrive without a carrier. A signal must move. A detector must respond. Energy must be exchanged. Even the quietest measurement is still an event inside the universe, not a view from outside it. This matters greatly when we approach the smallest intervals and the highest frequencies. To measure a shorter interval, the measuring process must be faster. To see a smaller distance, the probe must have a shorter wavelength. To distinguish finer details, the physical interaction must become sharper. For a long stretch of scientific history, that strategy worked beautifully. Better clocks revealed more precise time. Better lenses revealed smaller structures. Better detectors revealed weaker signals. The more refined the instrument, the more clearly the world appeared. But there is a point where refinement becomes disturbance. The energy needed to make the probe sharper begins to change the thing being probed. At the Planck scale, this is no longer a minor nuisance. It is the central difficulty. A measurement fine enough to resolve a Planck time or a Planck length would require conditions where quantum mechanics and gravity both matter at once. The probe would not simply bounce off a tiny object and report back. Its energy would help curve spacetime. Its attempt to define a position or a moment would affect the geometry in which position and moment are supposed to be defined. This is why the silence beyond measurement is not mere emptiness. It is the silence of a question that cannot be asked without changing the language of the answer. Imagine trying to measure the surface of a pond with a ruler. If the pond is calm, you can describe ripples, distances, and heights. If the pond is stormy, the ruler still works in principle, but the surface changes while you measure it. Now imagine that the ruler is so heavy that placing it on the pond creates waves larger than the ripples you wanted to study. The more seriously you measure, the less the original surface remains. At the Planck scale, the problem is far deeper than a heavy ruler on water, but the lesson is useful. Measurement is not always neutral. Sometimes the act of trying to know something becomes part of what is happening. This is one reason a faster than Planck rhythm may not be available to science in the ordinary sense. A rhythm must be observable, at least in principle, if it is to belong to physics as a measurable process. It must leave traces. It must be distinguishable from other rhythms. One cycle must be separable from the next. But if the cycle is shorter than the smallest interval in which our current concepts of time remain meaningful, then no ordinary detector can count it. And if making a detector energetic enough to count it creates gravitational effects that hide or scramble the signal, then the rhythm has moved beyond measurement in the usual way. It is not merely too fast for our instruments. It may be too fast for the framework of instrument, signal, and clock to survive unchanged. There is a difference between something being unknown and something being unmeasurable in principle. Many things are unknown simply because we have not yet found the right method. The inside of distant planets, the atmospheres of exoplanets, the details of ancient climates, the behavior of rare particles, all these may be hard to study, but clever methods can bring them into view. Science is full of discoveries that once seemed unreachable. But the Planck scale may involve limits of a more severe kind. If every attempt to probe below a certain scale requires energy that creates a horizon or destroys the clean meaning of space-time, then the problem is not only that our tools are weak, The problem is that the universe may not permit the information to be extracted in the form we seek. Black holes give us a useful example of this kind of silence. They are not silent because nothing happens there. Near and inside black holes, gravity is intense, matter can be heated violently, space-time can be curved beyond ordinary imagination, and quantum effects may slowly allow radiation to emerge. But the event horizon creates a boundary in what distant observers can know. Once something crosses the horizon, it cannot send a normal signal back out. The information is not available in the direct way we're used to. A black hole therefore teaches us that physical boundaries can also be boundaries of knowledge. The universe can have regions whose contents are not simply waiting to be seen with a better telescope. At the Planck scale, measurement may face a related kind of boundary, though not necessarily a horizon in the same familiar sense. The boundary may be formed by the combination of quantum uncertainty, gravitational collapse, and the instability of spacetime geometry. To look closer, we use more energy. Use enough energy in a small enough region, and gravity responds strongly. If gravity responds strongly enough, the region may become hidden, or the geometry may become too uncertain for the original question. The result is a kind of silence, not because reality stops, but because the path from reality to measurable information becomes blocked or transformed. This is humbling, because science is built on measurement. A theory may be elegant, but if it never touches observation, it remains incomplete as physics. The Planck scale is difficult because it lies so far beyond direct experimental reach, and because the usual road toward better experiments may not continue smoothly. We cannot simply build a microscope with unlimited resolution. We cannot simply build a clock with unlimited speed. We cannot simply pour energy into a smaller region and expect nature to give us a clearer image. At some point, energy itself becomes the obstacle. The lamp becomes brighter and then becomes blinding. Then, at the deepest extreme, the lamp may become a black hole. Still, this silence is not the same as defeat. Scientific silence can be informative. When nature refuses to answer a question in one language, it often suggests that a new language is needed. The failure of classical physics to explain the behavior of heated objects led to quantum theory. The failure of Newtonian ideas to handle light and motion at extreme speeds led to relativity. The failure of old models to explain atoms led to quantum mechanics. In each case, the silence was not empty. It was a sign that the old concepts had reached their limit. The Planck scale may be giving us a similar sign. It may be telling us that the language of waves in smooth space-time, clocks ticking against a background, and measurements made by outside observers is not fundamental enough. The word outside is important. In older pictures of physics, it was easy to imagine an observer standing outside the system, measuring it without being included in it. This was never fully true, but at everyday scales it was close enough. A person can watch a falling ball without noticeably changing its fall. A scientist can time a pendulum without becoming part of its motion in any important calculation. But in quantum theory, the measurement process cannot always be ignored. In gravity, the observer and the instrument have energy, and therefore contribute to the gravitational field. At the Planck scale, there may be no clean outside position. The observer, the clock, the signal, and the geometry are all inside the same physical story. This changes how we think about limits. A limit is not always a locked door. Sometimes it is a reminder that there is no hallway beyond the door in the way we imagined. Asking for a frequency beyond Planck frequency may be like asking for a northward step beyond the North Pole. The words make sense until the coordinate system reaches a point where the direction changes meaning. In the same way, asking for a shorter time than Planck time or a smaller wave than Planck length may use familiar words, but the physical setting may no longer support them. The silence beyond measurement is therefore not a place where the universe says no in a human voice. It is a place where our question loses its footing. This does not mean that nothing exists beyond the Planck scale. That would be too strong and too simple. It means that what exists may not be describable as smaller pieces of space, shorter pieces of time, or faster ordinary waves. It may be described by quantum relationships, information structures, causal connections, strings, loops, networks, or something no present theory has fully captured. The deeper reality may not be hidden like a coin under a cushion. It may be hidden like the rules of grammar are hidden inside a sentence. You do not find grammar by cutting the sentence into smaller and smaller letters forever. You understand it by discovering the structure that makes the sentence possible. This is a useful way to think about space-time. Perhaps space and time are not the most basic things. Perhaps they are what appear when deeper ingredients are organized in the right way. If so, then trying to measure below the Planck scale with ordinary space-time concepts may be like trying to find wetness inside a single water molecule. Wetness is real at the scale of many molecules behaving together, but it is not a property of one isolated molecule. Maybe time, as we know it, is real at the scale of clocks, atoms, planets, and memories, but not fundamental in the same way at the deepest level. The Planck scale would then be where the familiar property begins to dissolve into its underlying cause. This idea appears in several modern approaches to quantum gravity. Some suggest that space-time emerges from entanglement, the quantum linking of systems in ways that have no ordinary classical equivalent. Some suggest that geometry is built from discrete relationships. Some suggest that causal order is more fundamental than space itself. Some suggest that what we call particles and fields are expressions of extended or deeper structures. None of these ideas is settled as the final answer, and a sleepy narration should not pretend otherwise. But they share a common theme. At the edge of measurement, space and time may not be simple containers. They may be outcomes. If space and time are outcomes, then Planck frequency is not just a high number. It is a boundary between levels of description. Below it, or beyond it, the universe may not be silent because it lacks activity. It may be silent because activity no longer means cycles in time, waves in space, or signals moving through a fixed background. The deeper process may be real, but not rhythmic in the usual sense. It may give rise to rhythm only after space-time has emerged enough for clocks and waves to exist. That thought is difficult, but it is also strangely orderly. It says that our familiar world is not false. It is a large-scale expression of something deeper. There is a calm analogy in music, though we should keep it practical. A song exists when notes are arranged in time. You can hear melody because your brain can distinguish one sound from the next and remember the order. But if the sounds were compressed beyond any possible hearing or recording, the song would not function as a song for any listener. The pattern might have some mathematical description, but the musical meaning would vanish. Similarly, a physical rhythm requires distinguishable cycles. If cycles cannot be distinguished by any possible physical process because the structure of time itself is no longer clear, then calling it a rhythm may not add understanding. It may only preserve a familiar word after its use has ended. Measurement also depends on memory. A detector must record something. A clock must preserve the count of its ticks. A scientist must compare one reading with another. At the Planck scale, the energy needed to make a record may become part of the gravitational problem. Information storage is physical. It requires states that can differ. It requires stability long enough for the difference to matter. Black hole physics has shown that information storage, entropy, and area are connected in gravitational systems. This suggests that there may be a maximum amount of information that can be packed into a region. If so, there may also be a limit to how finely events inside that region can be distinguished. The silence beyond measurement may therefore be linked not only to time and energy, but to information itself. This turns the highest frequency into a question about the finest possible difference. Frequency means a repeated difference. One state, then another, then back again, counted over time. If the universe cannot physically support distinctions finer than a certain scale, then frequencies beyond that scale do not correspond to meaningful differences. They are like extra decimal places on a measurement whose instrument cannot justify them, except far more fundamental. In everyday life, adding false precision is a small mistake. At the Planck scale, it may be a category error. It may be pretending that nature has supplied a distinction where no physical distinction can be made. The great silence beyond measurement is therefore not a wall of darkness. It is more like a fog made of limits. Quantum uncertainty limits what can be jointly defined. Gravity limits how much energy can be concentrated. Relativity limits how signals travel and how time is compared. Information theory limits how distinctions can be stored and communicated. At the Planck scale, these limits do not sit apart. They overlap. Together they create a region where ordinary measurement loses its authority. Not because science has become weak, but because science has become honest about what its own concepts require. This honesty is one of the quiet strengths of physics. It does not simply announce that everything can be known if one is clever enough. It asks what knowing physically means. It asks what a clock must be. It asks what a ruler must do. It asks what a signal must carry. It asks whether the act of measurement can be separated from the thing measured. These questions are especially important in a universe where space-time is not a passive stage but a participant. The Planck scale forces that participation into view. For us, resting at human scale, the silence is harmless. We do not need Planck scale measurements to live our lives. The room around you is smooth enough. Time passes steadily enough. Your breathing does not require quantum gravity to continue. The ordinary world is not undermined by the mystery beneath it. In fact, the mystery helps explain why the ordinary world is so remarkable. From a deep structure we do not yet understand, there emerges a world with stable clocks, reliable atoms, shining stars, warm hands, quiet evenings, and minds capable of asking what lies beneath them. Perhaps that is why the silence feels less empty the longer we sit with it. It is not the silence of absence. It is the silence of a question waiting for a better instrument, or perhaps a better concept than instrument. It is the silence at the bottom of a well so deep that echoes return changed. It reminds us that the universe is not obligated to make every layer accessible in the same way. Some layers are seen directly, some are inferred, some are approached through mathematics, some are known by the failure of older ideas to pass through them unchanged. As we drift nearer to the end of this journey, the Planck frequency remains what it has been all along, not merely the fastest possible tick, but a signpost at the boundary of physical meaning. It tells us that a rhythm faster than this may not be a hidden song waiting to be heard. It may be beyond the conditions that make songs, clocks, waves, and measurements possible. The silence beyond measurement is not a final silence. It is the pause before a deeper theory, the quiet space where physics admits that time, at its smallest and fastest, may not be something we measure from the outside, but something that emerges with the universe itself. The silence beyond measurement is not a final silence. It is the pause that appears when our usual tools have gone as far as they can go, and the universe asks for a deeper way of thinking. After wandering through Planck time, Planck frequency, shrinking waves, black holes, and the limits of observation, we arrive at the last idea gently, not as a dramatic ending, but as a place to let the whole subject settle. The final tick before sleep is not a literal sound at the bottom of reality. It is the last clear tick our present physics can speak about before the language of ordinary clocks begins to fade into something not yet fully understood. A clock is a friendly object because it makes time feel orderly. It tells us that a day can be divided, that appointments can be kept, that trains can be missed for reasons that are at least numerically clear. A clock takes the enormous mystery of time and gives it a face. Even a digital clock with its glowing numbers gives the same comfort. It turns the flow of experience into a sequence we can read. Earlier in our journey, we followed that comfort downward, past pendulums and quartz crystals, past atomic clocks, past the rhythms of light and matter, until the clock became less like an object and more like a question. How fast can a tick be before ticking itself no longer has its usual meaning? Planck frequency is one answer to that question, but it is not an answer that closes the book. It is more like the last page we can read clearly before the print changes into a script no one has fully learned. If a clock could tick once every Planck time, it would tick at Planck frequency. That statement sounds neat, almost too neat, as though physics has placed a perfect tiny metronome underneath the universe. But we have learned to be careful. There may be no tiny metronome. There may be no hidden gear clicking away in the dark. What there is, at least in our current understanding, is a natural scale where time, energy, gravity, and quantum uncertainty become inseparable. This is why the final tick is not simply the fastest tick. It is the tick at which the idea of a clock begins to lose its independence. A normal clock can be treated as a separate thing. It sits on the wall, on a bedside table, inside a phone, or inside a laboratory. It measures time without noticeably changing the time around it. But a Planck-scale clock, if such a thing could even be imagined, would not have that luxury. To tick so fast, it would need energy packed into a region so small that gravity would become important. It could curve the space-time it was meant to measure. It could disturb the very interval it tried to mark. The clock would no longer be a quiet observer. It would become part of the mystery. This is one of the most important lessons hidden in the subject. Measurement is not free. It always happens inside the universe. A ruler is made of matter. A clock is made of physical processes. A detector responds through energy and interaction. At everyday scales, this hardly matters. You can measure a table without changing it much. You can time a kettle without altering the boiling water in any meaningful way, though watching it may make the wait feel longer. But at the deepest scales, measurement becomes active. To make a measurement sharper, we need stronger interactions. To resolve smaller intervals, we need higher energies. To probe shorter distances, we need shorter wavelengths. Eventually, the act of measuring begins to reshape what is being measured. That is why the Planck frequency is not just an extreme rhythm, but a warning about the limits of sharpness. The universe may not let us sharpen time without end, not because it is hiding a smaller tick and refusing to share it, but because below a certain scale, the old idea of a tick may not apply. A tick assumes a before and after. It assumes a stable interval. It assumes that something can repeat and that another system can count the repetition. If spacetime itself becomes quantum, fluctuating or emergent at the Planck scale, then these assumptions are no longer safe. The tick does not simply get faster, it becomes harder to define. This changes the way we think about the word possible. In everyday life, possible often means difficult but achievable. It is possible to climb a mountain, cross an ocean, learn an instrument or bake bread that does not come out resembling a geological sample. In physics, possible means something stricter. It means permitted by the rules of nature, and at the Planck scale, even that phrase becomes subtle, because the rules we know are incomplete there. Planck frequency may be the highest meaningful frequency, according to the way our known constants fit together, but beyond it we do not yet know whether nature says no, or whether our language has simply run out of proper words. This is a peaceful kind of uncertainty, if we let it be. It is not the uncertainty of confusion. It is the uncertainty of standing at the edge of a map drawn honestly. Good maps do not pretend to show lands that have not been surveyed. They mark coastlines, mountains, rivers, and then, where knowledge ends, they leave space. The Planck scale is like that blank edge on the map of physics. We have reasons to believe something important happens there. We know our existing theories point toward that region. We know quantum mechanics and gravity must both matter. But we do not yet know the full shape of the territory. Still, we have gathered clues. Black holes tell us that gravity can place boundaries around information. Their horizons show that what can be known depends on space-time itself. Their temperature and entropy suggest that quantum theory, thermodynamics, and gravity are deeply connected. Quantum foam suggests that at the smallest scales, space-time may not be the smooth stage we imagine. High-frequency waves tell us that shortening a wavelength increases energy, and enough concentrated energy can create gravitational consequences. Measurement tells us that no observer stands outside the universe with clean hands and perfect distance. Each clue points toward the same conclusion. The fastest meaningful rhythm is not just a matter of speed, it is a matter of what reality can support as a distinguishable process. That word distinguishable is worth keeping near the pillow for a moment. A rhythm exists for physics only if its cycles can in some way be told apart. One crest from the next, one tick from the next, one state from another. If there is no possible physical way to distinguish the cycles, then calling them cycles may not add anything real. At ordinary frequencies, distinction is easy. A pendulum swings left and right. A sound wave compresses and relaxes air. A beam of light has a frequency that can be measured through its interactions. But near Planck frequency, the cycle is so brief and energetic that distinguishing it may require a process that destroys the very clarity we seek. The final tick before sleep is therefore not only the last fast tick, it is the last tick that our present physics can imagine as distinguishable. This makes the subject strangely human. We live by distinctions, morning and evening, work and rest, memory and expectation, a moment before sleep and the moment when sleep finally takes over. Time matters to us because it separates events enough for a life to have shape. If everything happened at once, or if nothing could be distinguished, experience would have no order. A clock is useful because it gives order to change. Planck frequency asks what happens when that order is pressed to its finest possible edge. And the answer, for now, is that the edge becomes quiet. Not empty, not meaningless. Quiet. It is quiet in the sense that our instruments cannot reach it directly. Quiet in the sense that our equations become incomplete. Quiet in the sense that a wave shorter than the Planck scale may not be a wave in the usual meaning of the word, and a tick shorter than Planck time may not be a tick in the usual sense. There may be deeper activity there, perhaps a structure of quantum information, perhaps a network of relations, perhaps something our current imagination has not yet learned how to picture. But if it exists, it does not speak to us as a normal sound, a normal flash, a normal signal, or a normal clock. That is not failure, it is how science grows. When older language becomes too small, new language must be built. Classical physics could not explain atoms, and quantum mechanics emerged. Newtonian time could not survive the speed of light, and relativity changed our view of space-time. Smooth space-time and quantum uncertainty cannot yet be joined completely, and so physicists search for quantum gravity. The final tick before sleep is a reminder that science is not finished, and that unfinished does not mean weak, it means alive. It also reminds us that the ordinary world is a remarkable achievement of nature. We spend so much time thinking of the deep universe as more real than the surface world that we may forget how impressive the surface world is. Somehow, from whatever happens at the deepest level, there emerges stable space, reliable clocks, atoms that hold together, light that travels, stars that burn, planets that orbit, and minds that can ask about Planck frequency while lying under a blanket. The everyday world is not an illusion just because it has deeper roots. It is the large-scale form of those roots. A tree is not less real because it grows from hidden soil. So when we speak of the highest possible frequency, we are not trying to reduce the universe to one last number. We are trying to understand why numbers, clocks, and waves work as well as they do, and where their usefulness may end. Planck frequency is a boundary of description, a sign that above this rhythm, ordinary ideas may no longer remain ordinary. It tells us that time may not be infinitely divisible in the way imagination allows. It tells us that energy cannot be packed without gravitational consequences. It tells us that measurement may have a deepest cost. It tells us that space-time may have a hidden structure, or may emerge from something deeper than space and time themselves. There is a gentle comfort in the fact that we do not need to resolve all of this tonight. The universe has been carrying its Planck scale secrets long before there were clocks, laboratories, or curious mammals looking up at the sky and wondering why the night was so large. It will continue carrying them while we sleep. Physics is patient because nature is not in a hurry to be fully understood. Every generation listens for a little more, measures a little more, imagines a little more carefully. Some questions are answered, others become sharper. Some turn out to have been the wrong questions, which is often one of the most useful discoveries of all. Perhaps the question of a faster-than-Planck rhythm is one of those. Perhaps someday a deeper theory will say very clearly that no smaller interval exists. Or perhaps it will say that intervals themselves are not fundamental, and that time emerges only at larger scales. Or perhaps it will reveal that frequency, as we understand it, is a surface concept, like temperature or sound, real and useful where conditions allow it, but not meaningful beneath the scale that gives it support. Any of these answers would be extraordinary. Each would change not only how we think about time, but how we think about reality itself. For now, what we can say is enough for a quiet ending. The Planck frequency is the highest natural frequency suggested by the combination of quantum theory, gravity, and the speed limit of light. It is tied to Planck time, the smallest natural timescale suggested by those same constants. It is not a proven cosmic frame rate. It is not a literal ticking mechanism under the universe. It is not a sound, not a vibration ears could hear, and not a station waiting to be tuned. It is a threshold where known physics tells us to be careful, because beyond it the concepts of wave, clock, measurement and time may need to be rebuilt. And so the final tick before sleep is really a human image for a scientific boundary. It is the last clear tick in the story before we let the mind rest from trying to divide time into smaller and smaller pieces. It is the point where we stop forcing the universe to behave like a clock and allow it to be stranger than clockwork. The tick fades, not because time has ended, but because our familiar way of hearing it has reached its limit. If you are still awake, notice the slower clocks around you, the rhythm of your breathing, the small changes in the room, the faint movement of thought as it begins to loosen. These are not Planck scale rhythms. They are warm, ordinary, biological rhythms shaped by cells, nerves, memory, and the long turning of Earth. They belong to the scale where we live, and there is no shame in that. The deepest physics does not make ordinary rest less important. If anything, it makes it more remarkable. Somewhere above the unknown grain of space-time, above quantum fields and atoms, above the hidden architecture we have not yet named, there is a person listening in a room, slowly becoming quiet. Maybe that is the best way to end a journey about the fastest possible rhythm. Not by chasing a faster tick, but by returning to slower ones. The universe may contain a limit where frequency can no longer be increased in any meaningful way, yet life is not lived at that limit. Life is lived in heartbeats, footsteps, sunsets, meals, conversations, and the soft border between waking and sleep. We study the Planck frequency because it tells us something about the foundations of reality, but we rest in ordinary time because ordinary time is where experience unfolds. Wherever you are listening from tonight, and whatever the clock near you happens to say, you have travelled a little way through one of physics' deepest questions. From the smallest interval to the fastest rhythm, from waves too tiny to picture, to black holes that bend the meaning of time from measurement to silence. We have followed a single idea until it opened into many. If this quiet journey helped you settle, or gave your mind something calm and curious to hold, I would be grateful if you liked the video and subscribed. It helps this little place of gentle science find others who may also enjoy learning while the day grows dim. Now let the fastest clock in the universe remain where it belongs, far beyond ordinary reach, at the edge of what physics can presently say. Let the questions wait. Let the equations, which we have not needed to write down tonight, stay quietly in their notebooks. Let the black holes turn in distant galaxies. Let quantum fields do whatever they do in the deep places beneath matter. Here, for this moment, there is no need to measure anything more finely, no need to divide the second, no need to chase the final tick. The night has its own rhythm, and it is slow enough to follow. Sleep well, fellow traveller, wherever and whenever you are.